Hello, 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 and welcome. Welcome to the intermediate course for Grasshopper. And I know the video title says advanced course. That's the clickbait portion. We are dealing with an intermediate course right here. And before we begin, I want to say a few words in regards to this course and generally talk about what this course is about, and more importantly, what it's not about. So first of all, again, this is an intermediate level course, and if you're completely new to Grasshopper, I strongly suggest first finishing the introductory course, the beginner level course, which I have also uploaded to this YouTube channel, and I'll leave a link to it in the video description below. Second, the reason why this is not an advanced level course is because I think that at a certain point, at a certain level, you do need to learn coding, you need to start looking at APIs, you need to start scouring GitHub for snippets of code that you could adapt and so on, right? And on this channel, we are not nerds. We don't do any of that stuff here. Everything that we will do in the next couple of hours will be done only by using Grasshopper nodes. We will be downloading a few add-ons, but you know, that's kind of requirement these days. Third, the whole course will be divided up into these chapters, and in each chapter we'll be building off from what we did in the last chapter, right? So chapter 3 requires you to finish doing stuff that you did in chapter 2. So make sure that you're following the course accordingly. And by the end, we should reach something like this. A growing discrete block system that follows certain rules, recognizes collisions, and adapts to the limitations while still following said rules. At an intermediate level, you start to focus onto a certain field or a certain functionality. And I choose this particular one to teach you because it was my research for a year or two. While at beginner level, I could cover the whole range of nodes that Grasshopper has, at intermediate level, we need to focus on something quite specific. If you feel like this particular thing might not be useful to you, I'd suggest still giving this course a chance. You might be surprised by how much stuff shown here might transfer to any other project that you'll be working on in the future. And lastly, if you want to have the scripts without following the course step by step, or if you just want something to rely on if you'll get stuck, all of the files are available for Patreon supporters as well as paid YouTube members. Links in the video description below. And with all of that being said, let's jump right into it. Alright, chapter 1, the warm-up. The reason why I call it a warm-up chapter is because we are not going to be creating the script, the final script, in this chapter. Rather, we're going to be creating elements that will be brought into the script. And just give me a second, I'll show you what we're going to be coming up during this chapter. A few notes. The first one being I'm running Rhino work in progress, or Rhino 9, right? And this is just so that it's a little bit more future-proof. But if you run Rhino 8 or Rhino 7, you shouldn't have any issues whatsoever. The script that I have done for this course and where I checked was done in Rhino 7, which means, you know, it's compatible. So first step is to make sure that all of the plugins that we will be using are going to be available or are going to be installed. Package manager. Nope. Package manager. And search for ViewerBird. This one, install it. If you already have it, don't install it. Mesh edit. This one, install it. If you have it, don't. Anemone, install it. And last one is Fox, which does not exist in package manager, which means we will be getting it from Food for Rhino later down the line. So I guess I can quickly show you what we're going to be dealing with Give me a second. Boop. I have this as my note, I guess, as my notes. We're going to be making a box, but not just any box. Let me start showing you the functionality. The box will be able to do this. Morph into a tetrahedron, right? So that's an important aspect of it. And the second one is the box will be able to aggregate, grow, like that, right? So it kind of connects to its own sides, and then as it morphs, the aggregation changes, right? If I increase this to, let's say, 5 generations, and since from one box you're growing 2, right? And there is collision detection, meaning that it can't grow backwards in this case, but since there are 2 elements spawned from a single point, it has the tendency to do like an exponential growth, right? So as I'm slowly starting to change the angle of this, there is going to be a threshold, a certain threshold, at which there's going to be enough of a gap for another branch to emerge. Right there, right? And then as I keep pushing this, more and more branches emerge. And then you can actually see at a certain angle, we end up with a crystalline structure. And this was part of my research of trying to find these angles at which transforming a box into some sort of another platonic solid, where do these kind of converging angles lie? And in this case, it's somewhere close to 0.707155, something like that, right? So that means we're starting to form structural loops, and from these structural loops, crystalline structure can emerge. If I increase the amount of generations, you can see that it becomes a fractal self-reflect, or not fractal, but it's just kind of repeating itself as a pattern, right? But then as I keep pushing the angle towards the tetrahedron, which is not a space-filling form, this starts breaking down, and then we're back to a mess, right? So back here, from a line of boxes into, well, that's close enough, into a crystalline structure, into a mess. That's going to be our kind of core element with which we're going to play. So let's start creating one. I will, now you need to give me a second. I'll do that, I'll do that. There we go. I run Grasshopper and we begin. Oh yeah, and I have 2 anemones here, so I'm just going to replace all. Yeah, sure. There we go. So first thing is me checking if I have bifocals. I do not, goddammit. Give me a second. There's one plugin that I need to get here. Okay, so I just quickly installed it and restarted Rhino, and now I have bifocals right here. What these do is they just show the names of the nodes so that it's easier to follow along. Okay, step 1 is create a box. Actually, we are going to be using a domain box, I guess, or a central box. Let's do a domain box. Again, this is a intermediate level, advanced level tutorial, so course, so I'm not going to be explaining too much about the nodes themselves. You'll just need to kind of, if you're getting stuck, just follow along in terms of, oh, my English is breaking. No, not right now. First do the beginner course and then follow along with this one, right? I'll just do 10 by 10 by 10, just a cube, and let's find like a nice way to represent this. Something like that. Yep, I think this will be fine. So we have our 10 by 10 by 10 box. And immediately, in order to transform this, I need to work at a point level, right? So I will need to work with this at, as if it was points. So I will deconstruct, not box, but brep, to get the vertices out. And I have no idea which vertices are which, or rather, I have no idea which vertices need to connect how. So I would, if I were you, I would draw like on a piece of paper a diagram of how tetrahedron would fit inside of this box. But in this case, since I've already done it, you can just follow along and you'll end up with a tetrahedron as well. So what we're doing is now we're getting the points out. I don't even really need to see the box, only the points here. And I will split the list of points, so list item, into 8 outputs. 1, 2, 3, 4. There we go. 8 outputs. 8 points, 8 outputs. And I can do point list here and increase the size to like 2 or something to actually see which one is which. And this is 0, 1, 2, 3, 4, 5, 6, 7. And basically what I want to do is I want some of the points to move closer to other points, right? In order to kind of clamp down and flatten out the box, the shape. Sorry, I'm kind of messing this explanation up. Let me draw a diagram instead. Maybe that's going to be more helpful. If I do 10 by 10 by 10 box, extract silhouette, or is it just silhouette? Wireframe? Extract wireframe, yeah. I do that. Where's my gumball? Where's my gumball? There we go. Delete this. And here I have 0, 1, 2, 3, 4, 5, 6, right? So what I will want the tetrahedron to look like, let's just draw a surface and let's just get endpoint snap on. So I'll want it to go between 0, 2, and 5 right here. That's going to be one side of the tetrahedron. Then I'll want it to be 0, 2, and 7. 2 and 7. That's the second side of the tetrahedron. And then it's pretty straightforward, right? So the box should transform into this shape, right? Which means that point 1 needs to move towards point 0, right? Point 3 needs to move towards point 2, point 4 towards point 5, right? This towards here, and point 6 towards point 7. And once the movement is fully done, then suddenly we end up with a tetrahedron. Welcome to the intermediate course. Much less explanation and much poorer explanation, apparently. So actually, I'll keep it for just for now. So we're going to be creating that. I will, first of all, to move, let's say point 1 to point 0, I will just do vector between 2 points. And point 1 is here. So the vector is drawn from point 1 to point 0, like that. And I'm just going to multiply that vector by a number that is in between 0 and 1, right? So I end up with like a movement of halfway there in this case, right? And then I'll just use a move tool, move, enter. And the point that we are moving is point 1. So that connects to the G input of the move. Oh, it's going to be such a nasty. And vector connects to the, oops, not the vector, the multiplied vector connects to the translation input, right? So we end up with having this. Let me zoom in. Very simple. 1 moves to 0, right? So that's kind of step 1. Then we need to kind of do this for the rest of moves. So we did this move. Now I want to do that move, right? So the next one is going to be point 3 moves towards point 2. We just literally repeat the same process. Vector between 2 points, point 3 moves to point 2, towards point 2. We multiply the vector by the same number. You should not use like multiple different sliders. And we just connect that to another move. And in this case, point 3 is moved, right? And multiplication is added to the target. Or not target, sorry, to the translation vector, right? So now we have 3 moving towards 2 and 1 moving towards 0, right? We're basically skewing the bottom. 2 more of these. I need to move 4, this point, towards 5. So vector between 2 points, 4 towards 5, multiply by the same number, and we move 0.4 with this vector. We check again, always kind of check. So 4 is moving towards 5. It needs to be opposite direction from the bottom, because in the bottom it moves here, in the top it needs to move here. So we just kind of double check. Yep, exactly what we want. And the last one is going to be 0.6 moves towards 0.7. Well, move is going to be used later. Vector between 2 points. 0.6 moves towards 0.7. Gets multiplied by that nice slider that we have and gets added to the translation, and 0.6 gets moved. Okay, we're done with the moves. So all of our points are moving correctly. Now it's time to make this into a proper mesh. Yay! We will be merging the points back into a collection. Boop, 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 boop. One more. Boop. 8 points. And we'll just kind of connect them, I think, yeah, the same way, right? So point 0 was not transformed, so it just directly connects to the first input. Point 1 was transformed, so the move connects to the second input. Point 3, don't remember if it was transformed or not. Point 3 was transformed. So, wait, did I forget point 2? Yeah, I did forget point 2. Point 2 was not transformed, connects directly. Point 3 was transformed, connects, the move connects. Point 4, point 4 seems that it was transformed, so that connects, the move of it connects. Point 5, not transformed, connects directly. Point 6, transformed, the move of it, and point 7 stays, goes to D8. That's the assembly. Okay, having fun? Having fun yet? You should be. So let's now take a look at the points here after the transformation. So I'm just kind of removing the point list to show the points after they have been merged. Hide all of that, or actually show the final merge. And as I move the slider, yeah, that's exactly what I want to see, right? Maybe it's going to be easier if you see the box like that, right? So I end up with points here. There's a way of how to force the points once they touch to merge, which inherently messes up the, you know, if this is 1, then the points should not be duplicated, right? Only 1 point should be selected. But in my experience, that messes up our sequence of planes of the surfaces that we have, because tetrahedron has less surfaces than a cube. And because of that, it kind of messes up the amount of planes that we have. So we will not be doing that. We will let this be on top of each other, and just so that we don't have any issues with it later, we're going to limit the slider to a number that is very close to 1, but not exactly 1. But that's later. Okay, and now it's time to construct a mesh from these vertices, and we can just have fun with it. So let's do like a weird number here, and just kind of try to construct some sort of a triangulated mesh out of this, right? So right now, if I create a panel and I type in triangle, is it curly brackets or regular brackets? I don't remember. 0, 1, 2. Connect that. Oh yeah, okay, it doesn't matter. It's doesn't need to be curly brackets. So it creates a triangle between 0, 0.1, and 0.2. And to construct that mesh that actually is capable of transforming, we just need to kind of stitch it out, make it out of triangles. So that's 0, 1, 2. Then another triangle, 0, 2, 3. Doesn't work. Right click, multi-line data, force it into being in multiple lines. Now it works. Now we have 3 of them. If you don't see the mesh edges display, preview mesh edges. Now you see them. Then triangle. This is going to be a little bit trickier. I want, okay, 1 second. Need to see the box. If it's 0, 1, 2, 0, 2, 3, then it needs to be 0, 7, 3. 0, 7, 3. And triangle, let's just do 3, 7, 2. I'm sure that that's going to be necessary. 0, 7, 2. Let's take a look. No, it's not 0, 7, 2, sorry. It's 3, 7, 2. Like that. Let's do custom preview, just so that we see what the hell we're actually making. Okay, that's going to be easier to see. Now, as I am transforming this, see, that's starting to actually work. Okay, back in here. Then I want another one, 2, 7, 6, right? Triangle 2, 7, 6. Another one. There's going to be a few of these, so bear with me. 2, 6, 5. 2, 5, 2, 5, 1. Double check. Yep, we're still correctly kind of reconstructing the box, basically. 1, 5, 0. 0, 5, 4. Is it 4? I think it's gonna be 4. 0, 5, 4. Double check. Yep, that's fine. 0, 4, 7, clearly. And then the top is left. 0, 4, 7. And then for the top, triangle. If you want a quad, you can also make a quad. But in this case, since we're transforming it so much, it's better to triangulate it. 7, 4, 5. 4, 5. And then last one. So I'll start from 7 as well. 7, 5, 6. Oops. 5, 6. There we go. Yay, a box. Ugly one, but it is a box. And now this box has the potential to become almost a tetrahedron, right? Like that. Congratulations, you have successfully transformed it. Notice, by the way, how at 1 it's freaking out, and that's because some of these triangles are just overlapping each other and it's just failing to construct a proper mesh. Not a problem, we will be fixing that. So once this is done, we know for a fact that this is going to be like an item, a component that's going to be reused. So I'm just simply going to create a number for this, create a number node for this, Control Shift to reconnect or disconnect and reconnect all of the wires at the same time, and create a mesh for this, right? The reason why I'm doing this is because right now I'm going to drag the slider out here, drag the output out here, and I'll make this into a cluster. Much cleaner, much nicer, right? So that's basically my cluster, and if I look at the preview of it, why does it not show the, oh yeah, it doesn't show the preview because it's at 1, but here it is, right? And I can connect it like so. There we go. And of course the size of it can be changed. So I can right click, call it size. And this one, I can call it transform percentage. Cluster name, box 2 tetra morph. Output mesh. Okay, that's it. Easy. Don't really need the mesh here, so I'm just going to have it like that. Right. So now this slider, I don't want it to go, I want to limit it right before it gets to 1, because as we know, when it's 1, I already talked about it, it freaks out. So I'm just going to quickly do smaller than, if this is smaller than 0 point, 0 point, panel, 0.999999, something like that. Connect that. Then it should be filtered, right? That value should be filtered as this gate, and if it is smaller than this, then this should be used, and if it's not, then this should be used. I think this is how it will work. And now if we use this as a transform, yeah, it limits basically the number. You can see that if it's 1, if it's larger than this, then this is false and 0 input is used. If this is true, if it is smaller than this, then output 1 is used, right? So this is like a easy way to do a hard limit for any slider that you have. Okay, that's our transformation. It's ugly, isn't it? Ugly in a sense of shading. It's not being shaded that well. That's because it's welded. So we want to unweld the mesh. Bam, like that. And we just choose angles, or sorry, degrees. Use that as a custom preview. And for the degrees, set number 0. Gets unwelded, so the shading is proper. Yay. That seems to work. That seems to work fine. Let me check if Arctic view. Yeah, Arctic view is a-okay as well. Right. Okay, one part is done. On to the next. So now what we want to do is we want to basically grow this, right? And look at how it aggregates, and we don't need this anymore. Look at how this aggregates as it's growing. And there are different ways. Mostly we will be using Anemone for this, and we'll be automatically setting up, or not manually, sorry, setting up the growth. But in this case, we will be just using Fox plugin just to kind of speed up the setup process. And By that I mean we need to go to the internet, put for rhino.com, go here, search for Fox, bam, this one right here, download the Fox 1.01. It says for Rhino 4 or 5, it works for Rhino 8 for Rhino 7 for Rhino 9. We will only be using the aggregate version of this, so aggregation version of this, so there's no reason why it wouldn't work. And then once you installed it and once you restarted Grasshopper under Fox, we will be using create tile node, which basically asks us for the base geometry. So that's our element that's going to be aggregated. That's literally just our mesh. And it's going to ask us for planes, for different orientation planes, right? The first one is always the root plane, so from which the element is going to be taken, and the further ones are the target planes. So in this case, let's say you can take the element from here and then imagine using orient 3 points, reorient it to this plane and this plane. So the origin is here, the other two are here, right? So let's get the planes out. Delete that. To get the planes out, I need to, well, first of all, get the polylines out of this shape. And don't forget, this is not a tetrahedron, right? It has more faces than that, right? So I want to extract the polylines. We can do face polylines. We can do face boundaries or Weaverbird's face polylines. I'll just use the Weaverbird one, doesn't matter. So we get a bunch of polylines out, and then with list item, I will get the ones that I actually want to work with, right? So the trick is, I got cut off. Okay, where was I? The trick is to get the polylines that are responsible for the sides of the tetrahedron. We don't want to aggregate on the sides that diminish, you know, as the growth happens. We want to work on the sides that actually are left behind once we kind of converge everything into a tetrahedron. So 4 sides in total, right? To do that, we will use list item to get the polylines out. And for example, here I can see that this this polyline right here, polyline 0 from the face, is incorrect because it converges to a line during the full transformation from cube to tetrahedron. So that doesn't work. I can just do, okay, what if it's 1? Okay, it's still there. What if it's 2? There we go. That's one of the sides, right? And we can just kind of search for it by changing the numbers. Alternatively, you can always get an area, center point, point list, size 2, and it's just going to show you 2, 6, 9, and 5, right? 2, 6, 9, and 5. Okay. So if I then do this, 2, 5, 6, and 9, I just want them to be in the growing order. That will show me all of these three sides, right? Even before it's fully transformed. Oops, that's the wrong slider. Like that. Like so. All right, step 2, getting the planes out. So to get the planes out, I could just ask for is planner or is curve planner. Ooh, the planes are a little bit too big. So let's just display preview plane size. Let's change it to like 2 or something like that. The problem is that, this gives us the plane on the corner of these faces, right? We want the planes to be in the middle. If they're on the corner, that means it's getting moved from the corner to corner. We can't have that. So I could technically do area. We will be rebuilding this clearly. I can do area, and then I can do plane origin like that. And our plane is right here. And the origin is the center point, and now they're right on the, like that, the middle of these faces. And then from them, I could use like a list item, like so, and just get all 4 of them separated. So then I can just say the first plane is our initial object, or the initial plane from which all of the orientation is going to happen, and the next 2 planes are going to be the ones towards which the elements are going to be rotated. In this case, I'm skipping the last one. Technically, I could just add it in, right? But 1 to 2 is fine for now. Then we can just do tile t volume, or tile t, is it? Nah, let's just do tile t volume. T is the tile input, G is it needs to have like some sort of a geometry, so I can just make a mesh sphere. This is basically geometry in which the calculation is going to happen, and I'll just give it set number radius of 1000. That's it. And now we can start seeing the problem. Things are not aligning, right? We need to have more work. More work needs to be done with this, right? Things are working, but they're not aligning properly. So clearly the planes need to have more work. Okay, let's delete that. We still have those polylines, and now let's do it properly. So to get a little bit of flexibility, the first thing we need to do is we need to have these planes properly, all of them to be properly aligned. I will explode these polylines into their individual segments, and I will use evaluate tool, curve evaluate, or sorry, no, let's do evaluate length just in case. This gives me more consistent results. And the length to evaluate, this is still going to be a factor, so the number is going to be 0.5, middle of each of these. So I have 1, 2, 3 for each triangle, right? 3 points. And I'm simply going to if I have, sorry, now I'm a little bit confusing myself. If I have these middle points, I want to have a plane right in the middle, and I want it always to be looking at one of these middle points, because they're kind of, the same logic is applied to every triangle. And from it, looking at that point, I want to create a plane, which means that, let's say I choose this point needs to also be rotated around the middle by 90 degrees, so that I can get the X and Y angle, the X and Y direction for plane creation. Okay. You can see that in the beginner tutorial, I was thinking a little bit less than in this one. Or course, sorry, not tutorial. So since I have these, there is going to be a little bit of rotation involved, but first let's do list item, and let me just grab not the first item in the list. These seem to be a little bit bad. Let's grab the second item in each list. That seems to be a little bit better. So I'm going to be working with the second point. And at this point, since they are like just 4 points that I'm selecting for 4 polylines, I don't need them to be in separate data trees. The moment when I can get away from using a data tree, I immediately flatten the output to not deal with that. Okay, so that, I don't really want to see the tiles right now. There we go. We have our polylines, we have our, let's also have them a little bit like this so that you can see better what's going on. We have our polylines, we explode them, we get the middle points, and then we choose one of the middle points that is here. And that is going to be our X direction. Okay, let's create the quick center point. So for each polyline, I will just create a polygon center like that. And out of all of these, I'll just use the vertex average, this one. So that that is going to be the origin of our plane, right? Hopefully it's starting to make sense. This is the origin, this is the X direction, and now we will need to do the Y direction, right? If this still doesn't make sense, I can do plane 3 points, plane between 3 points, asks me for the origin, the X direction, and then what about the Y direction, right? If it starts from here and goes here, where's the Y? Is it this way or this way? So I want all of them to rotate the same way. And in order to do so, I'm going to ask for planarity, is planar or just planar. And I'll ask if these curves are planar, these polylines, if they are planar or not. I get the plane, and I'll just use rotate 3D. I'll be rotating my x-axis 90 degrees. So x-axis is the geometry that is being rotated. I think by default, this is 90 degrees. We'll see. The center point is this polygon center that we're using, clearly, because it needs to rotate around the middle of the plane. And the axis, I'm just going to grab one from the planes that we have created. That gives you the z-axis automatically, right? So once I clean this up, you will be able to see this is the origin point. Right now we're, let's say we're looking at this triangle, right? This triangle right here. And it has this point, and this point. So this is the origin point. This is the x-axis, so this is the direction for the x-axis, and this is the y-axis. If I do line origin to x-axis, another line origin to y-axis, hopefully that's even more clear, right? Once I connect the rotated, the end of the y-axis to the plane, these these 4 planes are created for me, and they are clean. And that's important. That's very important. So this is like just kind of not step 1, but generally this is the setup for aggregation, is because you want to have some flexibility. We will do a little bit more of our shenanigans, because right now all of these 3 planes, if I just do list item, bam, I separate them into 3 different or 4 different outputs, and I connect the first one to the initial input, second, third, and I look at it. Not great, right? Not great. It's still misaligning, right? There is some sort of an angle problem going on here that we will need to address. Thankfully, the angle is, what's the word? Consistent, right? So if one of these are kind of rotated, if the planes are rotated properly, then it should work. So what we can do is we can find that angle, right? That what's wrong with the angle by just simply, for the root plane, plane rotate or rotate plane, changing to degrees and using a rotated root plane. And let's just do 0.360 and start kind of rotating it until it aligns. And clearly it's going to be 90 degrees, right? Where it aligns. Yay, this works. Congratulations, this works. So I don't want a slider here. I'm just going to right click, expression 90. Because I know that, what? Oh, not expression, my bad, not expression. Right click, set number 90. Okay, so we have a little bit of growth going on and it's all aligned. And if I change the angle, that also somewhat works. Kinda, right? Clearly this is breaking here. We will need to investigate what's going on there. So a few more things to worry about, a few more things to fix. All of this information that you're kind of learning and that I'm giving to you will be applied in the future chapters. So we're not doing this for nothing, right? All right, let's do plane rotation. Actually, let's think a little bit. If I do, I kind of want to be able to experiment with these planes. And also one more thing is this should actually work on both ends. Why does it not? We're giving it all three. Oh, sorry, we're giving it only 3 planes. What if I give it one more? Yeah, okay, now it grows in the opposite direction. 1 second, just checking. That seems okay. Just wanna. Yeah, okay, actually that does seem to be a-okay. Except that it sometimes kind of grows and then it immediately stops growing. I think this is because it really doesn't like it that we are, what's the word? That we are touching the elements perfectly together. There is a certain amount of error that's going on in the calculation. So what we can do is we can make the planes be just a little bit further away from the elements, just a tiny bit. To do that, I will just measure the volume of the shape of the mesh that we have made. And for the center point, around the center point, I'm going to scale. That's going to be our center point. The planes by a factor of 1.001. So 0.1%. Just a tiny bit. Yep, immediately starts working, which is great. Then for plane 2, I won't be using that. I just want to I don't want to use too many planes here. So something like that. Why is this volume cannot be computed for open meshes? How are you an open mesh? 1 second, I need to check if I made any mistakes. All right, I'm not sure what's up with that, but seems like mesh volume is not complaining and just regular volume says that it's an open mesh, even though this is not an open mesh, it's a closed mesh. And mesh volume is just saying, yeah, that's fine. Both of them are giving me volumes though. So that's a double not being sure what the hell is going on. Anyway, just in case, I'm going to be using the centroid of the mesh volume rather than the volume. Should be fine. Okay, moving on. So I'm disregarding one of the planes because I don't want that kind of explosive growth. I'm just going to be using plane 0, plane 1, and plane 3, right? 0 is the root, plane 1 and plane 3 are the outputs, or not outputs, but the targets for the reorientation. Hide that. So now I'm just gonna borrow this rotate plane, and plane 1 should also get 1, right? And you can see here that it's clearly, you know, not every angle will work. So if I do the dot 360, if I do this and I rotate it, only certain angles for these triangles actually matches up, and some don't match up at all. Oh, god damn it. Okay, give me a second. I'm gonna check that one out as well. I remembered, or I found it and then remembered. If we have a midway transformation going on, right, the target angle will not, anything else than 0 will not align properly. 120 degrees, for example, should align, but it doesn't. It will not align properly because the proportion of this triangle, of these two triangles, doesn't match up, right? The proportion is not a tetrahedral triangle proportion, it's somewhere in between. It's like weird, right? And especially if I do 0% transform, you can see that, you know, we're off center, right? It doesn't work. But the moment when we go and become full on tetrahedron, then 120 degrees angle thing lines up, as well as 240, right? So this is just an inherent geometrical problem with, you know, transformation, and this not being like a clean triangle. It's a skewed triangle, or the proportion of it is not equilateral, which means, of course, then the angles will not match up. It is what it is. We can't have a lot of flexibility with these rotations. Not a problem. We're just gonna use straightforward elements or straightforward angles like so. Okay, let's move on. So the next step is to actually, am I recording? Yes, I am. The next step is to actually increase the amount of these. Now the functionality is there, right? All we need to do is just have more of them. So I'm going to create a slider 1.10. Those are the generations, or rather, yeah, 1.10. That's fine. So that's 2 generations, 3, 4, 5, 6, and so on, right? We have that. And then this closest points input is how many closest points should it kind of look at when it's trying to determine if it's colliding or not. And in my experience, 100 for something like this works fine. This is just an optimization thing, right? So something like that. Let's check out the transform again. Yep. Works exactly as it should. Moving on. Just to make it nicer, this is going to be the last thing for the warm-up. To make the preview nicer is I want to color the initial generation one color and the outermost generations another color, like make a gradient, right? So I'll be doing, I'll be extracting tree statistics. There it is, tree statistics. And the reason why I'm doing that is if we look at the data tree here, this is like first generation of growth, second generation of growth, third generation. So they are in their own little branch, and each of them, you know, so we just need to associate the branch number with the color, and you know, these elements will be colored accordingly. So once I have the tree statistics out, then I'll do a series from them. This just counts how many there are, and that's great. That's exactly what we want. So now we're counting 0, 1, 2, 3, 4 until 10. And I will be creating an RGB color. RGB. Alpha channel doesn't really doesn't get anything. Red, green, blue channels will though. So I'm just going to remap the numbers, this series. Sorry about that. I'll remap these series numbers as my values. I'll ask for the bounds of the domain of the series. So that is our starting or source domain. And the target domain is going to be 0 to 244 or 254, something like that. And that connects to red channel. And then I'll just do the same thing with the blue and the green and the blue channels, and we will be good to go. If it's only the red channel, by the way, and I just use that as my material. I can't use that as my material. I need to graft it. Data tree, don't forget. Then the initial element is going to be black. The outermost are going to be red. I don't want that. I want, you know, the initial one to be, let's say, blue, and the outermost ones to be red. So I need to remap numbers again. Same bounds though. So I can just kind of reuse this. And for the green slider, I'm just gonna give it, let's do 150 to 0. Let's just experiment. Okay, it's a little bit more green, yay. And then one more time, Control C, Control V. For the blue channel, it should be most blue early on, so 254 and none of the blue added, so it becomes this, right? So now with the green channel, I can control the brightness of it. If I do 255 here, right, it's like that. If I do 0 here, it's a little bit too dark, so we do want to inject a little bit of green into both. So I'll say 125 to like 30 or something. That's a nice color, something like that. And that's it. That's our custom preview. Last thing is preview mesh edges, also part of the Fox plugin. Tile connects here. And for the width, I'm just going to use 1. Don't need to display preview mesh edges here. That's it. Success. Generations are growing. Transformations are working. I can also write to here. Wait, I have notes somewhere here. 707155. So if this, if this is changed to edit more numbers, 0.707155, that is the crystalline structure that I have found. So this was part of my research for a while, for a year or so. If you want to continue on with this and playing around with it, do it. I want to see. I want to see how far you could push this further. For those who are interested, WordPress, that's the link. That's the research. That's those are the transformations, like different types of transformations that I've done, different types of like plotting out the densities and so on, trying to find something that creates structural loops. Yeah, so that's going to be useful for you if you want to kind of continue on this path. Right. If you find anything, write to me. We'll discuss. Okay, I think that's it. That's it for chapter 1. 1 hour, almost like 1 hour for it. Good. That means 10 more hours and we're done. Okay, I'll see you in the next chapter. All right, welcome. Welcome to chapter 2, I guess. Chapter 2 is going to be a big one, and I think it's going to be both chapter 2 and 3 at the same time, us creating a skeleton for the big script that we're going to be doing. In chapter 1, we have created this kind of we warmed up and created a little bit of a logic for the transformations and so on. We will be using this, but a little bit later. For now, for chapter 2, we just need to create a looping logic for growth. Actually, it's better to show than to explain. So let me just... This is going to be our chapter 2 and maybe chapter 3. We'll see how that works out for us. Okay, I need to type in Grasshopper. Boop, place that here. Or actually, no, that's fine here. Nope, I'll place it here. Logic is this. Let me turn this back. A bunch of curves exist. These are just hand-drawn, hand-drawn curves, right, in Rhino. And what this script is going to do is, as we are growing, right, the elements will be able to grow along the curves. In this case, the triangles, or not the triangles, sorry, the tetrahedrons will grow along the curves, and the moment they reach the end of the curve, they will be able to branch out, right? So a certain self-assembly logic, right? That's the aim, and that's what we're going to be doing. So for this, we will not be using the Fox plugin. We're rather going to be using Anemone, and that's because it enables you to have much more flexibility in in terms of the growth, and then the behavior of the growth. So if you don't have Anemone plugin manager, get it. Also, we will be using two more plugins, Lunchbox and Pufferfish, both available on Package Manager. Lunchbox, this one, Pufferfish, this one right here, right? So get those, install those, restart Rhino, you'll be good to go. Okay, let's begin. So loop start and end are clearly required for a loop to work. And as a beginning element, I'm not going to use the transformation that we have created before, or transforming element. Rather, in the lunchbox under form, I'll just grab the platonic tetrahedron from there. This is a brep. I want it to be a mesh brep, and I will use speed settings for just to make sure that it's definitely like these are separate polygons, and they're not divided up further, right? This is a single triangle, right? And then radius, let's just go for our trusty 10. Okay, that's our tile that we're going to be tiling. That connects to D0. Loop start and loop end connects like so. For now, we don't really need to connect them. I'll actually even delete loop end. We only care about loop start. Repetition. Repeat. Nope. That's just a slider. What am I doing? How many times will the loop run? I'll just do a slider between 0 and 1 and make it 0 so that it does not run for now. And then a button to trigger the loop recalculation. Actually, does this... Okay, if loop start is not connected to loop end, it seems like D0 will not spit out our little mesh through here. So I will do loop end, connect those two. Then we have D0. I connect them like so, hit it, run it. So this loop is basically it just taking the same shape and just here it is, 3 times, right? Because this is the first time it shows you, and then 2 more. Not much is going on here, but we can always, a little bit from the beginner course. If I move it a little bit and then I apply the repetitions, right? Whoop. Every time we're moving it by 10 units upwards. So that's how the loop kind of works. All right. So now from here, this mesh, the first thing that we want to do with it is we want to give it the possibility to branch out, right? And the branching possibility is going to be very similar to what we've done here with a few less steps, but sure. So first thing is, and I'm going to kind of be repeating it. You could just copy and paste it, but I'll repeat it because I think it's necessary to repeat things for people to learn. So, wait, 1 second. Sorry, apologies. 1 second. Is this 10 units? Yeah, that's 10 units. Okay, we're good. So step 1, mesh. We just get it in here. Then we get WB face polylines. We get the polylines, and we want to get the polygon center, like so. Also, we want to explode those polylines, sorry. We want to explode them, and we want to get the middle point of each segment. So I can just do curve middle as well. Curve middle. I think it's just under curve, right? So instead of doing the evaluate length, I'm just doing curve middle in this version. Then with list item, I'm going to get the second item of the list, and I'll just make sure that they're in the same list, all of these points. So four of them, right? So I just flatten the output here. Then I'll use rotate 3D. These points get rotated around the center point, the polygon center. Default angle is 90 degrees, so we don't change that. And then for the axis, I need the perpendicular 90-degree axis away from each surface. So I'm just going to ask if the curves are planar, get the planes through there. And once you feed the plane into the axis, which expects you to give it a vector, it's always going to take the z-axis of the plane as the vector. Right, so once that is done, I can create plane 3pt from 3 points. Origin is our center point. Bam. The x-axis point is going to be the one before the rotation, and y-axis point is going to be the one after the rotation. So we get ourselves the nice little planes. Remember this part? Mesh volume and scale, that's necessary. That prevents the floating point error from messing up your collision detection. So if you do it right now, you will be happy later. So for the mesh, I'll measure mesh volume, like that. That gives me a center point. I'll scale. Around the center point, I'll be scaling the planes. And the factor of scaling is going to be 1.001, like that. So 0.1% larger, right? Once that is scaled, then I will list item. I will divide up the planes. I'll separate out the planes into 4, like so. There we go. I have my 4 planes. And then the root plane, I need to have it rotated. Remember, we rotated it here. So I'll use the plane rotation so that things align properly. And I'll give it a -90 angle in degrees, of course, like that. And also, I need it to be flipped. So this create tile tool already flips our root plane. In this case, we need to do it manually. The reason why we flip it is because right now, all of the planes, the z vector of all of the planes, one second. Start, direction, length. My bad. Boop. So all of these planes are looking at the same direction. So if I just move this mesh from this plane to this plane, it's just going to kind of reposition this geometry so that it intersects with the original. I want the root plane to look inwards, and I can do that by I can do that by using flip plane tool. There's multiple that you can use. I will be using the one from pufferfish under plane. There's the flip plane one. And by default, it's already set to only flip the z-axis. That's exactly what we want. So now this plane is going to be, like the z-axis is going to be looking inwards. And that's excellent for us. That's what we want. Last thing to do is to use orient. The origin plane is our first one, the root plane. And the target planes are +1, shift +2, +3. So we're orienting it from this plane onto these three, right? And the geometry is, of course, going to be our mesh, long ass wire like that, right? So this original mesh gets oriented. That's it. We have ourselves a growth kind of step in a loop. I'm not going to be using that as a just exponential growth simulator. I think that's boring. We will be kind of more constrained. So for now, this part of the script is done. Let's create a mesh component, connect that here. And now we can actually select all of this and compress it into a cluster. The cluster is going to be called like branch out or something like that. Make sure that you name your clusters branch out. There we go. And make sure that you name your outputs as well, mesh. Okay, great. So now this mesh, as it's kind of growing out, will need to be, one second, thinking. As this mesh is growing out, it will need to react to the neighbors, right? So it will need to not be born if it's intersecting with any of the previous generations that existed before it, right? So we need to do a little bit of collision detection. What's the best way to do this? 1 second, I kind of need to think about this. I'll pause the recording while I do. Okay, I think I have an idea of how to drive this. So before we kind of continue, one thing that I want to do is write myself, as well as for you, a note. In total, we will have 3 inputs. We will need to have 3 inputs. One is going to be called, D0 is going to be called current generation. Current generation means that whatever is happening or decision making that is happening at the current like generation level. So steering, collision detection, all of that, right? It's going to be happening with the D0, within the D0 loop. D1 loop is going to be used later, but we're going to be using it for calculating, since we will be running it through multiple curves, not one curve, we will be calculating how many curves have been finished, right? How many curves have we grown through, or rather, that's a better explanation. At which curve we're currently at. Is it curve 0, curve 1, curve 2, curve 3, and then so on, right? So this is going to be true counter. And then D2 is going to be recorded generations, right? Recorded generations. This. Yeah, that should make a little bit more sense. So wait, I'm thinking. It's always, as it's kind of going along the curve, it's always going to have one element, one active element from which it branches out, right? So it's always going to, this is going to always be one single mesh no matter what. Then D1 is going to start with 0. Reset. Oh, it's complaining, right? Yeah, okay. This also needs a D1. Restart. Okay, D1 is going to start at 0. That's the current generation. And D2 is going to, we need D2 here, is going to start empty because nothing is recorded, but then these meshes are going to be, like all of the selected meshes are going to be added into the list. So we actually can already do a little bit of shenanigans with this. For D2, I can do geo, for short for geometry. You can just say mesh, that's fine as well. For now, I want to keep it flexible. And I can just simply merge. You know, the growth into the list. And at every generation, this is going to constantly be merged in. Hold your horses on that just for a second. We will be doing that later, but that's going to be the logic. Empty list, and we keep on adding the selected mesh to our list. The problem right now is if I have a curve like that, right? I first need to select which of these polygons or which of these elements are the ones that are steering closest towards the curve, right? Towards the tangent of the curve. So I think the first thing that we're going to be doing is we're going to be we're going to be creating the steering logic, and for that I need a cup of coffee. Sorry for this. It's a little bit complicated. 1 second, coffee. All right. So steering logic, huh? We have the branch out, but now we need to select one element that is the closest, that will be the closest along this curve. Yeah, not closest. Closest is bad, because if it's closest, that means it can be time to draw. If you have a curve like this and you have an element like that, and another element is, let's say, placed somewhere here, and then another element is placed somewhere here, and let's say from this element there's a possibility to create new one here, here, or here. You don't want this to be selected, even though this is going to be technically closer to the curve, right? You want it to constantly keep going forward. So we're not steering in a sense of it kind of trying to be as close as possible to the curve. We're steering it according to, I was using this as the origin, right? We're going to be steering it according to the vectors. Let's say this is the tangent of the curve, right? I know that is wrong, but and then you have 3 directions for where the elements are growing, 3 angles, right? Then you want the one that has the least amount of angle between the 2 vectors to be selected. Make sense? Hopefully it does. In doing so, you kind of eliminate this because this is opposite direction, and you constantly check which direction the curve follows. Right, so let's do that somehow. We have ourselves all generations out that are growing out from one, not generation, sorry. We have all of the elements that are growing out from the base element, which is here. So we're going to create a mesh node. We're gonna create another mesh node. So this is going to be called origin. I can't write. Origin element of the current gen. That's a little bit annoying. Let's do it this way. I should just delete this and do that. I'm going to group it instead and write a note like so. Origin element of the current gen. Okay, and this one is going to be called all permutations, or no, all variations after growth. So after branching, or after branching, I should say, after branching. And third input is going to be curve. And I'll call it current. Up, come on. Current curve path. Okay, we have these three. So we begin by taking the original mesh, origin element, right? And I'm just going to mesh volume, immediately get its center point, or volumetric centroid, right? And clearly it's just at 0 because it was created at 0. That's fine. Once that is done, I will also get the mesh volume of all of the variations here, and I'll get their center points, like so. I will measure, and then you can see them here, like that. So that's the center, and that's them. And I will measure basically these distances, right? That's what I drew for you. Not distances, sorry, these directions. I will create a vector between these directions. Vector 2pt between this and that. Whoop. Oh, that's a volume. My bad. Okay, I create a vector, and I mean, vector display should be fine. Vector display. Starting from here, vector is here. There we go. And that shows us these three kind of measurements that are going to be taken, and neither one of them are great for this curve, so I'm just going to make a better one. a better curve that once it works, we will know that it actually works, right? So this is going to be something like that. This is going to be our reference curve. I'm just going to create a CRV curve component, set one curve, connect that. There, yeah, that shows the direction. The direction is correct. Okay, so this step is kind of done. Then I want to, from the center point of the original mesh or original element, I want to find the closest point to the curve. Curve CP, nope, curve CP, curve closest point, okay, CRV CP, sure. From this origin point of the mesh to the curve, and clearly it just gives me right now the beginning of the curve, but sure, I can do something like this. I can do something like that. It's always going to give me the closest point, right? For now, I don't care. I just get a beginning, and I will evaluate. I will evaluate the curve, like so, at that particular parameter, right? So I get some sort of a tangent vector. Vector display. Boop, boop. Oh, it's super small, but you can see it, right? It's right there. This one right here. Maybe I hide these so that, yeah, now it's easier to see. That's the vector. So I need to measure the angles and find the vector that works the best. The angles are measured by the vector angle command, or just angle, isn't it? Yeah, it's just an angle command. And that's, we measure from this vector towards all of these vectors. We get some sort of a like angle in radians, of course. I don't like that. I will use degrees. Degrees. And the degree output is 3586,144. So clearly this is going to be the 144 angle. You know, the one that is pointing away from the vector, and these are going to be less than 90-degree angles. let's just run a filter of larger than 90 and just get rid of the crap that is larger than 90. Right now I have, no, it's not, no, it's not, yes, it is. And I will flip that logic. So this is true, true, false. So not, that becomes true, true, false instead of false, false, true. And I will use it to cull pattern. That's the pattern. And the stuff that we're culling is going to be our, are we culling? We're going to be culling all of the variations, right? So we're going to be culling away. Sorry, give me a second. Yeah, we can just cull the mesh. So we can just cull all variations after branching from those. It's a little bit messy, but it is what it is. We're going to be culling the one that is, you know, pointing in the wrong direction. So we're left with only these two. Basically, we're steering, or we're making sure that it's following the correct angle. If I change the position here, come on, or rather I need to rotate this, right? If this is rotated, it's going to be choosing the, like a different, what am I saying? It's going to be choosing different different elements that are aligned better with the curve, right? Okay, so cull does that. Then what if for some reason all of the elements, if that's even possible, are pointing away from the curve? If all of the elements that are growing at larger than 90-degree angle away from the curve, we need some sort of a failsafe for that. So I'm just going to measure the length, list length, measure the list length of after culling has happened. And if that is equal to 0, then I'm going to say, never mind, filter. So if that is equal to 0, then I will just say, wait, right now it's not equal to 0, so normal culled version is parsed. But if it is, I'm going to say never mind and just give me all variations. So basically turn off this whole steering thing and just give me all of the variations. And then let's just select the one that is closest, right? So that's the logic. Yeah, I think that's going to work. Mesh, place it there. And it's time to make another cluster, I think. Yep. So all of this, huh? Cluster that. Bring it in here. And I'm just gonna mesh curve. That's good. Or rather, I probably have to, the inputs and outputs of the clusters, I should name them properly. I'll name them properly. I'll just name this branching will be mesh, many mesh properly. And then here, current gen variations. So that's the many mesh, right? All of the possibilities are placed here. That's going to just current gen origin element or mesh. That's the original from which stuff grows. And curve is the guide curve. Okay. And output is cannot be freaking renamed. Let's go into the cluster. Can I rename you here? Can I rename you here? Hello? Fine. Mesh. Like that. Save it. Can I rename you now? No, I can't. Okay, fine. It's going to be S0. It is what it is. So now we have the original mesh and we have two elements that are not going in the wrong direction. That's the steering. So I'm just going to steer towards tangent, or just steer. And here, boop, and call this steer towards tangent. Okay, 2 clusters done. Next, we have 2. We can't have this as a branching growth. We want to select one, and clearly this is the winner, right? This is, even though this is still steering well, this is much closer to the curve, so we need mesh volume, or mesh volume. Like that. We get the center points of these 2 bad boys. We will just simply pull point. I think geometry is just going to be the curve, so I'm going to create the curve, put here. And it says closest, and it gives the distances. Yeah, okay, it gives us 2 distances. We will just sort. Yeah, that's easy. We'll sort the distances, and we'll sort the meshes along with the distances. So the one that is closest is going to be at the top of the list right here. List item, bam, mesh, bam. We're golden. We have selected the correct mesh. I mean, let's make things clean, right? Let's keep things clean rather. So, oh, not group, cluster. Like that. And this is going to be like choose closest or something. Choose one, and then group, choose the closest one, right? This is going to be variations, current gen variations. This is going to be guide curve. Output is going to be y. Okay, output, cluster output, mesh. Just want to name this properly. Okay, save. There we go, mesh. Okay. I think that's kinda it, right? If I were to just awkwardly connect this to D0, will this work? No. Why? Because this, okay, these guys want an input as well. Ooh, look at it go. And it kind of stops there. Oh yeah, that it stops there because I don't have enough generations. But now, yay, follows the curve, just like we wanted. I wonder what would happen if we have like 50 gen. Yeah, it just keeps going, doesn't it? Yeah, and that's because this guy, if we were to look at the steer, you know, it still finds that vector at the end of the curve and it just keeps steering according to it. That's okay. That's fine. So this works. This works. That means back to repetition, 10 repetitions. Now all we need to do is just save them, right? We need to like merge, not save them, sorry, merge them into one list, right? So we want to have all of the previous generations there. As I showed you, we'll be using merge. This is going to be D2 is recording generation. So our empty list, to our empty list, we will constantly be adding these meshes right here. I'll just force like a flatten on these two. No need the third one. And I will, just in case, even right now, if I look at this, actually not that bad. 1 second. Wait, empty data parameter. Oh, it doesn't give us a null anymore. Just in case, clean tree. Usually I use this remove nulls just in case there are any nulls. Doesn't seem like there are, but you know, just in case, you can never be too careful. 25. Congrats, we have successfully grown a piece of geometry tail looking thing. And now if I were to change the angle here, whoop, grows there. If I want it to grow up, whoop, grows there. If I wanted to make a weird ass bend, whoop, follows that. Hehe. All right, so that works. Let's make this pretty and call chapter 2 done. There's a lot of stuff still that we need to do, but the skeleton of our work is already kind of showing. It's great. This I want to just kind of group. I won't cluster it, and I'll just name it element recorder. And group color, I'll just change it to white so that it's easy to find, to see. Okay. 1 second. I'm just gonna think a bit. I decided that we're gonna be doing some coloring as well. Okay. So we have a bunch of stuff that is being recorded, and by a bunch of stuff I mean 26 meshes, not that many. Very simple. Let's do some simple coloring for here. We know that a mesh is coming out, or a list of meshes is coming out here. I'm going to get edges, mesh edges from here, and I'll just use custom preview on them with a swatch of black, like that. Simple. Just helps with the visualization. And then I'm gonna do some length. So according to wait, that's list length, yeah. So according to when the mesh was born, it's going to follow a certain gradient. So we're going to be using a gradient. That's not the one. There we go. That's the one. Very simple. Basically, the length is the max, and the color is going to be series along the length. So the count, it's going to just kind of keep counting until it reaches the end of the length, right? Yeah. Should work. This was the most horrible explanation so far, I think, that I've done. It's going to count until it reaches the end. List length tells me how many meshes I have. Series starts at 0 and counts, in this case, the same amount of times as how many meshes I have, how many elements I have. So it goes 1, 2, 3, 4, 5, 6, or rather it starts at 0. So 0, 1, 2, 3, 4, 5, and so on. Which then, if you assume that this is 0, this is 26, and it goes 1, 2, 3, 4, 5, 6, 7, 8, right? Until it reaches 26, I get equal distance colors associated with the meshes if I use the preview node. Custom preview, bam, mesh connects here. Needs to be hidden though. A lot of stuff needs to be hidden. There we go. Right. So that kind of works. Let's use a different different preset. Right. So now as it grows, good. It's going to be colored. So I think now we're kind of done. The initial mesh, we probably want to have that one kind of colored. Or wait, is the initial mesh colored? Sorry, I'm just kind of thinking. Actually, that's going to be chapter 3. Optimizations and making it nicer. For now, we made it work and it works great. No need to do anything else. So for now, chapter 2 is done. We move on to chapter 3. Bam. All right, chapter 3, let's go. So right now we have the base working, the script, the base of the script working. Let me just group this up, place this here, save it as chapter 2, and then Control C, Control V, make a copy of this and disable, disable the original. So chapter 1, chapter 2, chapter 3 is going to be this one. So we're going to continue on building on top of this. Right, what is missing? What do we need? The first thing is, well, the first important thing is the collision detection. Let's play around with this. Let me delete that curve and create a different one. Something like this. If I now set one curve, run this. Okay, that made sense. God damn it. That makes sense, but that's not what I wanted to do. Damn it. Let's try and force this thing to actually self-intersect. Okay, what about here? Oh my god, you're so annoying. What if this is a little bit higher up? There we go. And we need more speed, more. Bam, right there. So this should be accounted for, right? You cannot have two pieces of geometry just intersecting like that. You need collision detection. So this chapter is going to be about collision detection and also perhaps a few things to, make sure that the growth always reaches the end of the curve. So hopefully a short chapter, we'll see. Right, so for collision detection to work, we need to ask at every given generation, let's say first repetition, right here, we need to ask if all of the elements that are being branched out away from the cluster, if there is any intersection between the elements and the existing structure, existing element array, which is the D2 output, if there are any intersections between them, we want this to actually kind of those elements to be destroyed, right? And not to participate in further steering and so on. So like we add an additional filter. So let's just find the generation at which the intersection happens. There we go, question mark. Is that yeah, that is indeed, oh, come on. That is indeed an intersection, but I'm not sure if this element is actually chosen. Let's take a look. No, a different element. This one is chosen. So next generation, please. 75. 75 is, okay, all those two, and will an intersection happen? The hell? Oh yeah, okay, 76. There we go. definitely. So that's the element that is being chosen. This should not even be an option for it to be chosen, right? So now we finally can address this. Let's hide everything here and just take a look at the elements that are being branched out, as well as the already recorded. No, they should be here. Already recorded elements, right? So D2, if I just look at the mesh output here, is existing elements, custom preview. And our little branching out situation is hitting them right here. So make more space. We're gonna have a script going on here. For it to check, we need mesh and mesh. One is going to be all current gen variations. So it's these red ones, right? The output from branch out. And this one is going to be all recorded generations shunts, and it should be 1 second, thinking. Yeah, it should be just all recorded generations, right? All right. And then from this, I'm going to, well, menu mesh connects here. That's straightforward. And I will just simply check for the volume, mesh volume. I like to work with the center points of the geometries. For platonic solids, it's ideal. For more convex concave geometries, it's not ideal, but it is what it is. And here I'm going to ask if the mesh inclusion, if this mesh, these meshes, sorry, the D2, like that, if any of these meshes include this center point inside of themselves. So in this case, I'm only checking for the center point, right? That's an easy check. And this basically means that if there are no intersections between two meshes, they can either be away from each other or they can be inside of one another. And if they are inside of one another, then this will trigger a true statement, right? So I'm going to mass addition, like perfectly inside of each other, right? Not colliding. We have mass addition, result is 0. I will just ask if it equals, if this equals to 0. And that statement that we have is going to be, we want this to be false, right? So I'm going to take this as the output. False, right? Why are there so many zeros here? Does this need to be grafted actually? 1 second, thinking. Here we have, yeah, because here we have 3 volumes that we're checking. This does need to be grafted. Right. And now we have false, false, false. With a bunch of zeros for some freaking reason. I really don't like that. Where the hell does that come from? I actually want to check. 1 second. No, that's clean. That's clean. That's not clean. D0 is not clean. So D0 for some reason keeps creating these zeros for every generation. So I'm just going to do one little thing, which is called simplify, or I can do that here. Simplify. And that will just force the address of the data tree to be still shit. What? Wait, let's run this again. Huh. Can I flatten this? And not simplify this? Yeah, okay. Right. Anyhow, We have, I just flattened it so that this is cleaner. So that's one. Second one is all recorded generations. We basically just want to take the current gen variations, scale them, again for the collision purposes. Scale them just a tiny bit around their own center points by, let's say, 0.95 or something like that. And then the scaled versions of these will be used for collision detection. So I'm just going to ask for MMX, mesh collision. And mesh collision is going to happen between these three meshes. Again, I need to graft them, separate data trees or data branches, and I'll check them along with all of the rest of the all recorded generations, right? So I get my answers here, and the answers are just going to be empty since they are not colliding, except for right here, the polyline curves that are created here. And that's going to be sufficient for it to trigger. I just need to trim this. I need to simplify this so that there's no trash in the address, and then I need to trim data tree or trim tree. Take a look here. And now I know that element 0 has no collisions, element 1 is generating polylines, and element 2 has no collisions. So element 1 is the problematic child here, right? Okay. I will just ask if it's, again, equals. If this is equal to 0, and I just get, oh yeah, list length, sorry, list length. Nope. Because I just care if it's 0 or if it's anything other than 0. So I get my true, false, true statements right here. I want it opposite. I want it false, true, false. So I use the inequality option here. Like that. Okay, we're getting there. And if either one of these two statements is true, then it should turn true, because true means remove, right? So if you're inside of another element perfectly, you should be removed. If you're intersecting with any other element, you should be removed. So either this or this. So I need to use or, gate or, and this gets connected, and I get my little answer here. So basically, if this was true here, then you would have true, true, false, if that makes sense. You know, if this is true, false, false, and this is false, true, false, then this is true, true, false. Now we don't need the data tree anymore. We flatten this and we cull. We use this to cull. What do we cull? All current gen variations. We cull from those, and we, god damn it, and we end up with the one that is problematic. So this needs to be inverted. Not gate, not like that. So other two are culled, and the problematic one is left behind, just like that. And that's not going to be considered in the further calculations. So now we can mesh, create a mesh here. And this whole logic, I think we're kind of good to go here. Just gonna cluster this, see what happens, like that. Plug it in like that. So after branching out, collision detection happens, and then it starts steering, right? Run this again, and immediately it just breaks. Why? Because this is empty at the first generation, right at the start. This is an empty list. Since this is an empty list at the start, Then here, this produces, 1 second, thinking. Since this is an empty list at the start, this is empty, empty goes in here, and then the output here is null, because this is null. So this cannot be empty. Okay, let's return, and we need to solve this at generation 0. All right, let's think this through. 1 second. Actually, it should work. It should work. So even when it's empty. So I think the trim tree is messing us up. Because if I look here, mesh inclusion, bam, that's all good. Mass addition, bam. That's all good, question mark. But then we just, if since it's null, the inequality just gives us null, and gate just gives us null, gate not gives us null. Maybe that's bad. But either way, this orange part is where I don't like what I see. Because this should give us, the list length should give us 0, trim tree should give us 0. So I think this simplify is messing us up. Yeah, because right now that seems to work. Because even empty stuff, right? I still get 0 here, and since there are zeros, I get false here, nothing gets culled. It passes the first generation. Reset. And after it passes the first generation, it keeps going. Okay. And did it collide? It did not. Were we at 76? Okay. So this actually worked. And trim tree. Did I even need to use the trim tree for this? 275. Yes, I did. So the zeros don't matter for the trim tree, which is interesting. Okay, that's good to know. I didn't know that. I thought that you need to clean up the address more for trim tree to work, but it seems to be doing just fine. So you don't need to simplify it before you add the trim tree. Okay, so that seems to be working. It removes the problematic child, and then it just continues steering. So we're good on that, and then just continue. Great. Okay, so step 1 done. Can delete that. And now it's the fun time of collision detection. And then, do I need to name this? I don't. The output is meshes. That's meshes, and that's also meshes. Okay. Do we need, like, we can just do this, I guess, to clean it up. Double click on the line to create a relay to clean it up a bit. And then we have a mesh here. Don't need that. Just making sure that stuff is somewhat clean. Okay, so we have branch out. That's, I'm just gonna call it growth in all directions. If intersect grow inside of previous gen, then die. Okay, so we have that. I think we can, now it's time to move on. Where's my notes? I have my notes somewhere here. There we go. Okay, all right. So for this one, I also want to do a little bit of counting, or rather checking if we have reached the end of the curve, right, of this particular line. And if we have, then it should trigger this execution end or exit state. So we can we can do this in multiple ways. 1 second, thinking. Okay, let's do it this way. So if, first of all, let me grab the endpoints of the curve right here. Those are, and I just care about the end point right here. I can just ask if the closest mesh that was chosen, this one, if that is mesh volume, I love this one, mesh volume, center point, if that center point of the mesh is closer, length or distance, to the endpoint than our given variable. So smaller than, let's say, 10, right? So that's our given variable. And also I can just circle. I can just draw a circle, CNR, around the endpoint, just showing the radius that we have selected for the checking. So if the center point of the element is within the radius, then this should give us a Boolean statement out, like so. Right. That's gonna be our another cluster. Let's force it. So okay, 105 or 101. Boop. Is it? I'm not sure. What does this give us? True. So that already spits out a true statement, which means that the distance is indeed less than 10, 8.74. Okay. So since this is true, then we can just force that Boolean into the exit mode. And then no matter how much I increase this, this is still, that's weird. Okay, that's good. I just needed to restart. Once it reaches, it's going to stop computing, right? Because it reached the end. Good. We have a trigger for when we reach the end of the curve. So now it doesn't matter what's the number that we're using here. All right, cluster time. So I think for this one, I'll just use a number here. Like that. And what do we have? We have curve input, we have mesh input, we have number input, and then we have Boolean and curve out. I guess we can just do this as a cluster. And I'm just gonna call it mesh. That's gonna be curve. And that's gonna be radius or threshold. And that's going to be circle. That's going to be true if and reached. Curve and check. And then we group this and call it, how do we call it? Check if the curve end is reached. If near guide curve end, true, else false. Okay, this should give us a good clue later down the line what the hell is going on. So that, and then we don't really need a Boolean in between. We just directly connect it there. The curve is just whatever. It's just a preview thing. So I think I'm going to, I think we're just gonna use a custom preview node like that and hide that wire display hidden. Just bring it somewhere here. and call this curve and display, and this is going to be called element coloring. Since this is chapter 3, I'll change the gradient to something a little bit nicer. Also, I'll take a look at why this is orange, by the way, but that's later. Black and white. So why is this? That's orange now. Not orange. All good. Okay. Never mind. So this seems to be working exactly as we want it to work. We have 2 more clusters. Not this one. This one. And wherever the other one is, the collision detection. And I guess that's it for chapter 3. Okay, as I said, it's a little bit shorter of a chapter, but quite a necessary one. Next up, we're gonna do more than one curve, right? We need to be able to grow and branch out to multiple curves. So that's gonna be our chapter 3. Are we in chapter 3 right now? Chapter 4, I guess then. Which chapter are we in? Anyway, end of the chapter, and the next chapter begins now. It's chapter 4. Yes, chapter 4 time. So now as per usual, we group this, we save document as chapter 3, available for Patreon supporters. And then we just make a copy of this, disable the calculation of the original, and break the group so that we can build further logic here. Right now we only have a single curve going on. I want 2 curves. I want, or 3 or 4 or 20. I want a bunch of curves that would require the element to branch out like this. Because right now it's, what the, oh, right. I actually have to give it the curves. Set multiple, these 2. Those are the ends of the curves. And if I just, did it freaking miss the, oh god damn it. I didn't realize that it can also miss the damn end. So we need to either have a smaller element or more or larger curves so that it doesn't miss as much. Whoa. That's weird. So basically now it's using, okay, yeah, it's pulling itself to the whatever the closest point is. So there's no hierarchy between the curves. It doesn't care about finishing either here or here with either one of these curves. It just kind of uses both of them. So naturally the whole logic that we have built is only working with a single curve. Set one curve, run this, works. Yeah, okay. And then if I clear values, set one curve, run this, also works, right? So what we want is, we want this to be the first curve, this to be the second curve. And once it reaches the second curve, or once it reaches the end of the first curve, once it just goes until the end here, then it should choose from all of the elements that it currently has, one that is closest to the start of the second curve, and then it should branch out from that and continue on until it reaches the end of that, right? That's the logic. How do we do that? Good question. Let's think. So first things first is this. When this becomes true, it's already true, right? So as long as this is false, the element chosen should just be the same. Okay, we're doing a filter, clearly. Filter, stream filter. As long as this is false, so 0 input is the regular mesh, right? I think so. Yes, the regular mesh is just chosen as the next thing that is going to grow out, right? That is going to populate. But if this is true, then it should find an element that is closest to the next guide curve. So I should, the next guide curve is going to be this. The mesh is going to be the all recorded elements up until now. So that's just D2, right? That's the 81 meshes. I think so. Wait, for this one, I'm gonna check my notes. Yes, my notes say yes. And it's going to be not just D2, but it's also going to be D2 plus whatever was already added in this generation, because it might start branching out from the end of the curve, right? You should not disregard the final element. So it's going to be this mesh plus this mesh right here. Okay, so all of them. So out of all of these meshes, I want to ask endpoints, which one of these mesh volume are closest distance to the start of the curve. And I want to sort them, sort the distances and the meshes along with the distances. And I want to get the one that is closest, list item 0, index 0. So this guy right here is the closest one. Okay, makes sense. All right, easier said than done. Now, this doesn't work because we have one referenced curve here and one referenced curve here. I can't just keep referencing curves separately. So we want to have a certain way of how to kind of choose which curve we have. And this is where past me did a good thing, true counter. So instead of us stopping the simulation here, right? Instead of us stopping the simulation once we reach the end of the line, we will instead add a number to the true counter, which is right now set to 0. Good thing I'm doing clusters. Imagine this without clusters. So logic is this. We're growing, and at every loop step, as we're growing along this curve, it should keep spitting out 0, 0, 0, 0, 0, right? So we keep adding 0 plus 0. So plus 0. But then the only time when we reach the end, we say, no, it's not 0, it's plus 1. So initially we just increase it by 1, and also we trigger this, the finding of the closest element to the curve. So it goes, as this grows, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 1, 1, 1, 1, 1, 1, 1, 1, 2, and then 2, 2, 2, 2, 2, 3, and so on, right? So to do that, I need a filter filter. And if this true when then reached, if this is false, wait, do I have a filter here? Why do I have a filter? Mesh is parsed. I'm getting tired. Oh no. I'm getting tired. Help. Why is there a filter? When did I add a filter? Did I add a filter here? No. I'm just gonna delete it. Too many things at the same time. Okay, back to here. So this, at every generation as it grows, it's just 0 because we're nowhere near the end of the curve, right? So it's 0, 0, 0, which means we are checking, our filter is checking according to that curve end check. So it's constantly 0, 0, 0, which means that then if it's 0, we don't add anything to our true counter. So we keep adding in 0. The moment when it reaches the end and it's 1, we add 1. So as this is going to be growing, it's going to become 1, and we're just gonna stream filter suddenly will add +1 to this. And the new number is going to be connected to D1 instead of this kind of direct loop. So here, carefully like that, that connects to D1. Okay, so this should work. Probably. I'll just group this so that it's a little bit more clear or cleaner, I guess. And I'm just gonna name this every time end of curve reached +1. Okay, so that's our counter. Let's restart. Okay, it should be +1 now. So this number, okay, you can stop growing now. This number, which number is it? Data. This number is now 5. What the hell? How is it 5? Why are you 5? Okay, let's look at it closer. Okay, it's 0. Still 0. We're not reaching the end. We're not reaching the end. Not reaching. Okay, we're really close to the end. 81. Still not the end. 82. Okay, now we have triggered the end check. 83. Ah, 84. Okay. That means we're just kind of creating a bunch of elements at the end. So 5 elements in total crossed this area. Okay, that's fine. Because the moment when the end is reached, right, 1 + 1 number is created, and then we can have a list of curves rather than one curve. So, you know, two curves, for example. And once the end is reached, we just use this number, right, at 82. 1 second. 0, 0, 0, 1 as the index of the curve. Does it start to make sense? So if I have curve, set multiple, this is the first one, this is the second one, right? This is curve index 0, and this is right now at 1. Come on. This is right now at 1, but as long as it's 0, with list item, this is green. The moment it reaches, this turns green, right? Because suddenly list item fetches the second item in the list, which is our second curve. Okay, so in doing so, we are basically we can just connect it like that. And is that going to be curve +1, right? That should be curve +1. So that should be pop +1. like that. Because it's the next one, right? It's not the current curve, but it's the next one that we are calculating the growth towards. Okay. What's the okay? The correct curve has been selected, I think. No. The correct curve has not been selected. Because this is like the current curve, and this is going to be the next curve. I have to mark this. Okay, needs to be cleaner. All curves. Current curve. Current active curve or whatever. And then next curve. Okay. And now the problem is that the next curve kind of loops around, and it loops around and it's still kind of using the active curve. So how do we... 1 second, I need to think about this. Remember the filter that I deleted? I remember. So when we need that filter, filter, and I'll explain it again, mostly for myself so that I don't forget. Jesus Christ, I need a break. After this one, I'm taking a break. The quality is diminishing. So if true, if this is true, then instead of this mesh should be used, and that is going to connect to the D stream filter is going to connect to D0 like that. This is what it's doing. Let's run this. Okay, that's great. That's exactly what I want to see, except that freaking... the next curve triggers correctly here at the correct like generation, I guess. So it should be 81, right? So at generation 81, this curve is correct. This is still false, I guess. No, it's true. Yeah. This is true, which means that this is fetched. And since this is fetched, it's going to start branching out from this. And the current curve will become the next curve. Okay. So that actually works. It's just visually, it was a little bit confusing for me. So now this is still the current curve, and this is the next curve. But in the next generation, since the loop needs to kind of close and come back here, this is going to switch to 1. So this is going to be the current curve. And the next curve, since this is wrapped, this is technically going to be the back to the first one, but we don't care. Because we're going to have one more test here. Ooh, a little bit convoluted, but fine. So, hey. There we go. 100. Okay. And I guess now, yep, that's the problem. Now this can keep going. Oh, this one missed as well. All right. So that doesn't really work that well. And it doesn't work because there's no stopping, right? Once it reaches the end, then it kind of starts with this generation and keeps on repeating. Thankfully, the collision detection works, and there's no collisions between the elements, right? It doesn't choose the incorrect elements, so that's fun. but we need to have an end statement or some sort of an end goal for this to actually stop itself. So what we should do is just measure the length of the list and ask if equals if the current number of data of D1, which is true counter, if this number equals whatever number if this number equals the amount of curves that we have, that means we should stop the simulation like that, because we start counting from 0, and basically once we reach 2, that means 0, 1, and then once it hits the 0, 1, once it hits the end of this, triggers 2, and 2 triggers automatically the end calculation here, or not calculation, but the trigger for the end right here, like that. Very messy. I'll clean it up actually now, but let's try this. Does it thing? Does it thing? Dies. Good. Managed to branch once? Okay. Yeah, sure, whatever. But generally works, right? Works as expected. Let's clean this baby up, because right now it's a mess, and then let's play around with this a little bit. So step 1, this thing right here, I'll just call this find element that is close to the next guide curve or something like that. Should filter be here in part of the calculation? No. Kind of want it to be separate. So only this will be used, and this mesh goes here. Okay. And then cluster that. So this is going to be called next guide curve, and this is going to be all recorded elements, and the output is can't change it, that's fine. Branch position, and group this and name this find element closest to the next guide curve. Okay, so that, and it kind of lives here awkwardly. Don't need this. This is kind of clean enough. Don't really need to have it cleaner. That seems to be fine. This is not nice, but I don't know where to put it. Okay, I'll just put it somewhere. Element recorder should be higher up. Sorry. Somewhere here. And I wonder if element recorder... Yeah, still the closest element is chosen. Okay, that's fine. So this goes somewhere here. Group that and call this if end of last curve reached, then true. And then it just feeds into the exit rule. Okay. Is it possible to clean it up more? I mean, thank God for clusters, but Jesus Christ. Like that. Every time and curve reached +1. Yeah, this one also needs an explanation. So this is going to be like, if not end of curve, do nothing. If end of curve, pass the element element closest to the next curve. Apologies. All right. So, I mean, I can't make a shorter sentence than that. I think this is the cleanest that we will get this. Why are you orange? Oh my god. Never mind. It's fine. Pop. All right. So let's mess around with this. Why not? So here I just had a few curves here and there. Let's do boop, 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 boop. Boop, 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 boop. And actually, can I move this up and down and over like that? And you go higher up. And can I move this over here and then actually force a clump of things and a very, very sharp turn as well. Whoop, like that. And just, no, more intersections. Like that. And then this goes down actually, and I still want to force an intersection, so it goes through here. Okay, that clump is going to be a mess. Let's try. Set multiple. We start from this one, we go to this one, then we end with a very sharp boy. Died. Don't need those two. Died. Restart. Okay. Okay. Right. More generations. Huh. That's a weird path to take, but hey. No collisions. Very hard to see if there's any collisions or not. Let's big this out. Insert. Cell mesh. Move this away. Shaded view. Clipping plane. You are colliding. Wait, are you? No, you're not. You're just kind of touching. Are you? No, that's yeah, that's fine. Okay. So there's no collisions. Great. Cell dupe. No duplicates. I guess that's it. That's all I care about. No collisions, no duplicates. Curves worked out, and it's twisting its way through the whole kind of problem by also not colliding. Okay, that's our chapter 3. Chapter 3 done. Next chapter is going to be building up on this. Clearly. What else are we gonna do? So, see you in wait, this is chapter 4. See you in chapter 5. My mind. And chapter 5 is gonna be tomorrow morning for me. All right, chapter 5. We begin with a little bit of optimization. And actually, we begin by doing the same thing, copy paste, disable, remove group. All right, so until this point, what the hell is it? Ah, okay. Until this point, we have successfully grown a structure along a shape, a curve. That's kind of underlying. Just gonna check. Is that branching out? 1 second. How many curves do we? Oh, we have 3 curves. Okay, so it is branching out. All right, and everything works, but it could be faster. So one of the main things that kind of take a long time to do, if I look at the profiler here under growth, actually, Why does it not show up? Hello, profiler? Am I losing my mind? It should show, right? Well, let's try this again. Look inside. Nope. Anyway, doesn't matter. It takes a while to calculate the collisions, the collision detection, right? So we want to optimize that. Specifically, optimize this area right here where it's measuring mesh-to-mesh collisions. We don't want those to happen. It shouldn't try to kind of create mesh and mesh collisions to everything, right? Or calculate to everything. We want to limit the amount of elements that our initial mesh is checking for. So I guess let's clean this up a little bit. Here, this part right here, I'll just call this, group that, and I'll just call this inclusion detection. If you have a big element and a small element goes directly into the big element and it's not colliding with the walls, this would still throw us a cull request, right? And then here, I guess scale doesn't really matter as much. I wonder if we can get away without having the scale. Let me just double check. Apologies if this is a little bit confusing, but since we are offsetting the planes, I don't think this will do anything. So if I just save that and reset it, does it still work? Yeah, and now from here, yeah. Okay, so that scale was not necessary. Great. It's a little bit cleaner now. And this part right here, that is collision detection, right? So we have these two logics going on. So for the collision detection, I want to limit the amount of neighbors that we have. And the first thing is we should grab all of the recorded generations, like so. We have all of the current generation variations, like so. Well, right now it's at the end. Let me just save and close and just do like 50 repetitions. Let's say we're here, right? Back to collision detection. So here, again, all current variations are here and all recorded generations are here. And I can see that the last one that we have here, that is going to be, or is it the first one? Yeah, I should be removing the first item on the list because it starts with being empty. And if I have a null will mean that it's just going to throw an error. Okay, so we will do cull index like that. No, sorry, not the first, the last item. Cull index, reverse the list, and I'm just going to say the culling index set integer 0. So initially what I'm doing is here we have all of these generations, and here I'm just removing the last one from the list, right? Maybe it's gonna be easier to see like that. So from here, I'm just removing the last one. Okay, one more time. All recorded generations are here. Look at the last one. It's gone here, right? We're not going to calculate it because it already exists as a current gen variation. That's the reason why. We don't need it. Okay. Off to a good start, right? So now we measure mesh volume for all of these elements. And the mesh volume gives us a centroid, and all we need to do is just measure a distance to the mesh volumes right here. Distance. And since here we have 3 potential directions for where this can grow, those need to be grafted. and measured independently to all of the center points here. So we get a bunch of distances. I can also draw a line so that you can kind of see what I'm talking about. Graph that. So all of these three potential elements here basically measure their distances to all of the rest, all of the other elements. Still not great, but once we only kind of check for the ones that are the closest, should be okay in terms of the performance. So we're measuring the distances, right? Then I will sort. That's not how you. Then I will sort the distances, and together with the distances, I will sort the all of these elements like so. I end up with whatever 3 branches, and I will split those branches at a specific index. And that specific index, I kind of want it to be a variable, so I'll just do number, and I'll do input, cluster input, like so. Drag it over, let's see here. And that's my split. After the split, and for now I can just say 5, just to check. So now I have 2 data trees, one with, for every element, it just gets 5 closest elements to it, and the rest are located here, right? So from those 5 elements, all I need to actually do is just use those instead of the original mesh, right? So I can just simply, wait, how does this look like? Not great. I'll just simplify this, and I'll connect that to the B input. So now 5 comes in here, 5 comes in here. We have 3 data branches, empty intersections. That seems okay. Just in case, I'll simplify this as well so that the data trees match up. Yeah. And then for this one, I guess this just straight up goes into the mesh input here for the mesh inclusion check. Also simplify that. Again, data trees, the addresses need to match up. Once that is done, I can just input right there. This will start complaining because on the other end, this does not have a number. That's fine. I will group this up, and I will just call this limit neighbors. I think we're good to go with this. Okay, save that. New input, call it, what do you call it? Neighbor limit neighbors to check. Let's call it how many neighbors to check. Okay, sure, it's gonna be a long one, but at least it's clear in terms of what it does. Relay, okay, this is starting to get a little bit cramped, so so I'm going to just give it a little bit of space. Usually I would use the Alt key and, you know, expand it like that, holding the Alt key, but in this case, since I have so many scripts above it, I don't want to do that. Okay, that, and then give it a slider of 20 or panel. Whenever I can not use a panel, that just, or sorry, a slider, then I immediately use a panel because it saves space. All right, run this again. Seems to work exactly as we want it to work, but let's wait until it actually... I'm looking at the number here, 10 milliseconds, 8 milliseconds. Yeah, that's not bad. Okay. So the collision detection seems to work, and now it has been optimized, right? Now we can move on to the next kind of step. So is my camera lagging? Wait. Okay, it looks like it's lagging. Oh, whatever. I'll check it out later. I should check it out now. No, I'll check it out later. Okay. Next up, we actually will be using our initial morphing, like the morphing script, and we will be looking at how we can replace the tetrahedron with some other shape. And generally, I think the first thing that we should do is we should rewrite how the planes are fetched, because right now growth in all directions here, in this case, like the tetrahedron, right, that is simple because it always uses the same angle, right? But the moment when we are dealing with for example, a triangular prism, that is going to start becoming real nasty real quickly. So let's try what's a good way to do this? 1 second, I need to think about this. All right. I think I have it. I think I have an idea. Let's make a Tetris block. And we're gonna do it actually in Rhino, not in Grasshopper, because it's gonna be faster in Rhino. I'm just going to make a rectangle anywhere, doesn't matter where, anywhere in the world. I'm going to make a rectangle that is 10 by 10. And I'm just going to make a planar SRF out of it and copy. Hello, copy. And endpoints on, and just like that, like that, and like that. L-shaped Tetris block. Then I should make a top for it. So I'm just going to grab this whole thing, gumball, Alt key, and just bring it up 10. So I have the top and the bottom, and now this is going to get a little bit weird, but I will just loft between the edges here, to have these separate surfaces. So I don't want a straight surface. I care about all of these different elements, right? I want all of them to be squares because, well, it just, 1 second, loft can't talk. It's because if I have all of this divided up into squares, that means there are more possibilities for the geometry to actually connect to itself. And also things will align because every single square of this shape is exactly the same size. So as long as we're playing around with the 90-degree angles and the center points of these squares, things should align. I will join this up. And then back in Grasshopper, somewhere below the script, this is going to be like a little bit of a setup. I'm going to create a brep component, set one brep, and gonna make a simple mesh from this. All right. And actually I'm going to, let's just do it this way. I'm going to create a mesh container out of the simple mesh, right click, internalize data, delete, delete. And now we have our geometry inside of Grasshopper that is ready to go. And if I preview mesh edges, that's how it looks like. Okay. So now, step 2 is to know which face is which. I'm just going to grab mesh normals. I think that's the fastest. Or is it face normals? Yeah, it's face normals, because that gives me center points, and I will just ask for point list, and size like 3 or something. And I get my numbers, right? Okay, so that part is simple. Now the tricky bit. For each of the face, I need to have instructions on how it should connect to anything else, right? How these faces should connect. And these instructions are not going to, well, they're easy, but there's going to be 18 of them in total, so we need to get going. In order to do so, I'm just going to create a quick script, basically borrowing from the logic that we have right here, growth in all directions, the logic that we're doing here, but I'm going to make a more simplified simplified version of it, just to check what angles can be used on each of these, and also kind of decide on which one is going to be the root of it, right? So give me a second. I'm just going to think about this. All right, let's do it this way. If I grab my mesh, I can get its polylines. I think this is going to be faster. Face polys. I get the polylines, I explode them. The reason why we're not just simply doing like get center point, create a plane, is because I want this to work on triangles, on quads, and on like n-gons as well. So we need to have a more flexible solution to this, and I think this one is going to be the best. Curve evaluate, or evaluate curve, or I can just do a midpoint. Curve middle. For the segments, I get the middle points. List item, I get the second item on the list. We've done this already 3 times. I will just flatten that list so we have 16 or 18, sorry, points here. Then I will get a polygon center. Nope, from the polylines, right, like so. So I get the center points. Well, what else do we need? We need to ask if it's planar to get a plane. And the plane will be used to rotate 3D. So we're going to be rotating these points around a center point at the plane Z axis, like that. So we get a 90-degree angle, and then I just do plane 3 PT. It's the same thing as what we have done right here. This part. I'm basically repeating this part. But here to check, to have like a checker for which plane does what, I think it's a good thing to just have it separate. And then the origin is going to be the center point. Then we have the x-axis, the y-axis. We have our little planes here, right? For each surface. All right. Since we have the planes, we then want to use the orient tool. Orient. And we want to split the planes. Sorry, so it's list item. We want to use the list item, and we just want to have all of them out. I know this is going to be a little bit of a yikes moment, but you only need to set it up once. Should have used a little bit of a simpler shape now as a in the retrospect, but it is what it is. The orient is our G right here, and now we have our ABC, or sorry, AB. So the A, our root, is something that we always kind of consider, and that should be the first item in the in our list, right? And the first item in our list is going to be, let's think, which element do I want to connect it from? So for example, let's say I want my root plane to be index 8, right? I want to always, when I take the style, for this to always kind of be connected somehow onto a copy of itself. So that is this guy right here, right? Index. Yeah, that's just going to be plus 8. Yeah, this one right here. And I want this to be flipped. Okay. Let me just go to pufferfish plane, flip plane, like that, and that's our root. And then our target is it can be like plane Y, for example, and it connects nicely. Or plane 0, I should say. And it connects nicely. It can also be rotated, right? So now what we can do is we can create some sort of a logic with, in this case, it's just going to be a single root and multiple like variations of how it can rotate for any branch. But later we'll be able to use multiple roots. So for now, actually plane rotate like that, degrees. And then we do, it can be 0, 90 to 70, and that's it. 360 is the same as 0, right? So we will do series, or no, we can just do 0 dot dot 2, 0, 90, 180, no, 0 dot dot 3. Like that, and we can just multiply by 90. The b is 90, right? So we multiply by 90, and now we have our rotation. So for example, 0 works, 1 doesn't work, so 90 doesn't work, 180 works, 270 works, right? Makes sense? Starting to make sense? Okay, so what I want to do is I want to create a panel where I will say, or a data tree, Entwine. I will want to create a data tree where the first, like a list in the data tree is going to be, the first item on the list is going to be the root plane index, which is going to be 8, right? Because that's our root plane. And then following that, I will have all of the further, or all of the branch planes listed. So 8, and now we're at 0, like that, multi-line data. Don't forget to use multi-line data. And then the second entwine, or second entwine input, is going to be the rotations, I think. One second, I'm thinking. So 8 and 0 will have rotations of 0, 90. Wait, 90 didn't work, right? No, 90 didn't work. 180 and 270. 0, 180, 270. So if we have like a movement, not movement, but orientation from plane 8, the root plane, to plane 0, then we have these possibilities for orientation. But then if we have another one, let's do one more. And then we will start kind of rebuilding this script with the new logic. If we have another one from 8 to, let's say, 13, then I need to check. So instead of 0, I connect plus 13 to the plane rotate, and I just check for intersections. So 0 doesn't work, 90 works, 180 works, 270 works. So this then becomes 0 doesn't work, 90, 180, 270. So every other entwine input is going to be relationships, and every other is going to be the angles for those relationships between the two planes. First is the root, second is the branch. You can also have multiple branches. So for example, if I look at plane 1 here, 0 doesn't work. Okay, 90 doesn't work, never mind. I need the numbers to match up. So let's say +2, 0. Okay, that one also is annoying. God damn it. +7. Let's try that. Okay, 90 is fine. 180 is bad. Okay, I give up. But if there are any angles that actually would match up the behavior, you could just simply add one more number to this list, right? Because the first one is the root and the second one is the target. So this is where which angles does this relationship work at? Okay, hopefully that makes sense. So since I've built a little bit of it, let's see if we can actually make this a little bit cleaner, a little bit nicer. This of course is part of the script. Okay, we have our mesh. We have our face polylines, explode, curve middle. So we don't care about any of these. I just need to copy this. That means I just need to copy this mesh and use it here. This is just our testing area for creating these instructions. I'll clean it up later. So we have this original mesh. Let's hide that. We have the mesh and we have the instructions. What do we want? How do we want to prepare this tile so that it can grow on here? Well, first of all, the mesh is right now in Grasshopper and I can't easily move it. So we want to have it kind of move more nicely to the start of the first curve. So I'm just going to create a curve component. We have our mesh. We have our curve component. The curve, all curves go into this. And from it, I'm just going to, if I have a polyline, I'm just going to, just for the sake of it, explode it. But then from all of the segments, I'll flatten that out. I'll just choose list item. I'll just use the first item in the list. And I'll use the end point, or start point, sorry, of it. And for the mesh, I'll just measure the mesh volume as per usual. A vector between 2 points. And to the start. And then I'm just going to move the mesh by the vector. So it's always placed at the start of the curve, no matter where it is. This, I think we can just call it, and the output is a mesh. I think this one we can just make into a cluster because we will be reusing this like crazy. So I just make this into a cluster. 2 inputs. If you get like 2 inputs like so, you can always just do that, since it's the same mesh that's being volume checked and moved. And now it's going to be a little bit nicer. Actually, no, that stays here. So now we have a mesh that always will be placed in the correct position, right? Next up is going to be our entwine. And honestly, I think, I think we just give it like a data out. And we just straight up make this into another cluster, right? Because what else do we need? We don't really need much. This is a referenced mesh, or integrated now mesh. So I'm just going to call this guide curves for position. Mesh is going to be called, or cluster is going to be called Tetris L tile or element. Then the output is going to be geometry output, as well as the like plain instructions output. So the data that we get again important, is the first branch is the plane numbers. The second branch is the angles that you can have. Third branch, plane numbers. Fourth branch, angles that you can have for this relationship. Okay. So with that done, this is our like library element. Now we can feed this into our, instead of our platonic tetrahedron, which is also a library element, but it's very simplified. We can feed this L shape, right? So mesh goes in here. Now if I run this, it's not going to work, right? Because the planes are out of whack. So it just kind of keeps growing in the wrong direction. So we will need to work on that. You can even see here, like the way of how it kind of connects. It just kind of immediately connects downwards. That's fine. Growth in all directions needs a little bit of more input, I guess. So we're gonna give it that, because I have this data to work with. So first of all, I'm just going to, for branch out, I'm going to just give it a cluster input, because I'm sure that that data will need to come into this branching out cluster. And it's a data structure, so I can immediately do tree statistics. That's definitely going to be the first thing that we check. Save and close. I have one more input, and I'll call this instructions, plain instructions, or whatever it's called. How did I call it here? Yeah, plain instructions. And that data will just connect to here. I think that's fine. It feels like it's fine. I'm thinking hard right now. I don't need that. And this can just be directly connected like that. And curves are a little bit annoying, but I'm just trying to find a place. Okay, sorry. Okay, plain instructions should be the correct name for it. Okay. So now how do we rebuild this in order for basically this part, the orient part, to operate with the plain instructions that we have created? Well, first of all, we need to separate out which ones are the planes and which ones are the angles for the planes, right? So to separate it out, I will just cull nth for the paths, because here I have the paths. I cull nth, and I will cull every second one. Set inter. Oh, it's already 2. Very good. I'm culling that, and then I will just use split. I think it's compound transformation. No, split tree, or is it split list? No, it's split tree, I think. Split tree. Tree to split is going to be our input here, our data tree. And the mask for splitting is going to be the culled, like these two, right? And according to it, I get a positive part of the data tree and I get a negative part of the data tree. So every second branch is, I basically just fetch every second branch here. Also, the addresses are a little bit, I don't like maybe it's not a problem. For now, I'm just going to take a look or make sure that match tree, that the addresses are always correct. So I'm going to match the plain portion of the data tree to the split angle portion of the data tree, like that. No, opposite. Angle portion to the plane portion, and then check the angle portion again. 0, 0, 0, 2, 0. Okay, so now we have the addresses that are matching up for these guys. And at this point, I think I can start extracting planes, at least with this part, right? So I can do list item. Oops, that's the item index, right? Not the list itself. And where are our planes? Here. But also then we scale them, and we're doing all of the shenanigans. I'm going to delete it like that. Scaling. For this shape, scaling is weird because the center point, mesh volume center point, is located here, so it's going to scale awkwardly, right? It's not a platonic solid. It has a concave portion. So instead of scale, I'm actually going to, and then mesh volume, I'm actually going to check. I already have these planes. I can just move them along their z-axis away from the mesh. So amplitude, that's the vector, and the amplitude is going to be like 0.01. Very small number. And then I just move. Should have done this before. Okay, now it's more elegant. Now they're just kind of being moved away. Again, plane connected to a vector gives the z vector of said plane. Said not z, but of the plane that I have referenced. Okay, so now we have our planes. I think we just straight up just connect them like so, and yeah, we're just grabbing the planes from this list of all of the planes. We're grabbing the plane number 8 and whatever the other one was, plane number 0, and then plane number 8 and plane number 13 in a separate data branch. Yay. Okay. And then for these planes, I always want to grab the first item in the list item. That's going to always be our root branch. And then I want to get all of the other items. So cul index. Right now, it would be the second item on the list, but what if you have 5 items in the list? You want to get the 4 other ones. So cul index set integer 1. And thus we get the second item, or sorry, index 0, not 1. I'm stupid. Okay, now we get the second item in the list. So this is going to be our root, which means I'm just grabbing the flip plane, and I'm not really doing much with it. This is going to be our branch, which means I'm going to be plane rotate, or rotate plane. Switching this to degrees, and straight up just connecting the angles here. So these planes get rotated. 1 each, 3, 3. So I should have 6 planes here. And I do. Okay, amazing. Okay, that's good. I think we're okay with this. We can now just orient. Geometry to orient is our initial mesh. Root plane, the flipped plane, and target plane, the plane after rotating. Planes, multiple planes after rotating. Doesn't look like there are going to be any intersections. But there might be a problem with us not giving it too many options. We'll see. Save and close. We have our many mesh and repetitions 2. Holy shit. Oh, broke away. I think we're reaching a part where it can't grow because it does not have enough freedom to grow. Okay, 10. Oh my god. 9. 7. Okay. So clearly it works, right? It connects here, then it's managing to connect here, then it does the L shape here, L shape there, keeps going, going, going. And I think actually right now, this is giving 2 numbers for some reason. Okay, troubleshooting time. But this time I'm not pausing the video because I think this is going to be important. So let's take a look. Here it's giving us all of these options there. Collision detection is not removing any of those options, which is, by the way, what the hell? Why are you? Oh yeah, okay, you're there because I'm looking at you there. Are there just like 3 meshes that? Yeah, it's the same mesh just being added like 3 times. I think. So that's weird. Why does it do that? Shouldn't you be null plane? Okay, why the hell are you null? And this whole part is null. Is it because of the previous? Something that happened previously? Because here the logic is still the same. The planes here seem to be 18 is null. How are you? Why? What the hell is going on? Okay. Actually, I'm keeping this in the video because I think this is important. This is how I troubleshoot. I go back 1 step. That's still red. Okay. I go back all of the steps. That's still red. I go back to step 0. That is still freaking red, which indicates to me that something's fishy here. Is that still gonna be null? No, it gives us proper answers. Okay, so this works. What does this give us? Everything's fine. This, everything's fine, but here it kills a bunch of stuff. Why do I have a data tree here? Why is this a data tree? It should be 1 list. It's freaking out because it eliminated like half of the planes here. Okay, so if I go in here and I just simply flatten the output of the orient so that the many mesh output is actually just a single list, and I run this again, this is not complaining anymore. Yeah, that seems to be working fine. Let's take a look. Where's my curves? There they are. Okay, and then it freaks out still. We'll need to look at that. So after 70, I'm just gonna look at which step is it freaking out at. 49, huh? Yeah. So 48. More troubleshooting. What's happening on 48? True. True is reached. And since this is true, the filter passes this new branch position. And which mesh are you? You are this mesh. Understood. And you are messed up. It's impossible to grow from you. Okay. So since this is like in the next generation, when this is passed through 49, many mesh, and then after collision detection, it just goes, I can't. There's no way for me to grow without intersecting with my neighbors. And since we don't have a branch, it just shits itself. Okay, that's gonna be chapter 6 to solve it. To solve so that it doesn't shit itself. But for now, we can do back in here a little bit of not experimentation, but additional functionality. We need the plane 14. how do I look at this? So here, we need plane 14 as a root. Okay. To connect to plane 15. That's going to be a long L shape. So if that connects, wait, I'm being stupid. Plane 14 root, plane 15 rotation. And I think this one will have all 4 possible rotations. Yes. This should unlock a lot of possibilities. So this was just me checking, right? And now what I can do is I can go back into this Tetris tile cluster and I can write new instructions for it. 4 and 5. So this is going to be 14 as a root connects to 15 as a branch. And then 14 as a root will have all possible rotations. Okay. Are you gonna keep growing? Yep. Change direction. Yeah, there we go. And it broke. Okay. So still not enough flexibility. It breaks when it still does not have enough kind of places where it can go. But that element 14 or plane 14 has a lot of potential. So I'll also add it to plane 17, right? As a possible, I should just have it here like that. Plane 17, like that. And it also can do all of these rotations. So this is where actually it's useful to have this setup. Because right now all I need to do is just add 17 here. And that's it. Right. I don't need to create a new rule set because it's going to be 14, always the root, 15, 17, the branches. I should write it somewhere here. Scribble. Data tree logic. Let's just say like this, 0, 0, plane indices, or index, just index. First, always root, all others are target branches. 0, 1 equals angles, all possible angles for the growth. 0, 2 plane index, 0, 3 all possible angles, 0, 4 plane index, etc. Okay, this should be useful. All right, so now I added one more possible growth, which should be sufficient for it. Oh, it actually is going. And it missed the last. God damn it. And it missed it. Actually, to go back here. If it's missing it, we can check closer or at a larger threshold to the curve. So I'm just going to do 15. Okay. So 1 or generation 0, generation 1, generation 2, 3, 4, 33. Branches out, finds a way. Okay. Since we have enabled it to make a long ass line, whenever it will be able to, it will, right? Which is fine. I think that's part of the charm of these kind of scripts. But now we're getting somewhere, right? Okay. One more thing, and then we will finish up with this chapter. So for now, that's all curves. That's geometry. We don't have the initial tile from which we start, so I'm just going to connect it to D2 input, because D2 is the record generations, and that's just going to be our initial tile. Also, I'm just going to make a geometry node, connect that there, and data node, connect that there, and just call these inputs. We're always going to have these that they have these as our inputs. The bifocals are a little bit starting to get a little bit annoying, so I'm going to remove them. All right, we have ourselves a growth structure. So now tetrahedron, right? Let's do the tetrahedron thing and then move on. So for the tetrahedron, I'm just going to borrow the cluster where, oh, I should name this, sorry. Move to start of curve. Okay, I'll copy this, and inside of the, or not inside of the, but here, I'm just going to paste it. Move inside of curves, and I can just connect it there. So now, don't want to see that. Hello, where's my freaking output? Oh yeah, it wants me to give it a curve, of course. Plop. The tetrahedron is placed, right? So we have that. That's good and all, but now I want to create that entwine logic, that I had for the Tetris tiles. So I'm just going to actually borrow it. I don't want to do too much from scratch. So I'm gonna borrow this, and tetrahedron is gonna be easy. So the entwine, it's always going to be a 60-degree angle, and it's never going to self-intersect because it's a platonic solid. So, or is it 60? Or is it 30? Oh crap. Oh crap. It's neither. It's going to be 120. Okay, screw it. Let's check. So here we have our checking script, right? So very easily, I can just take my tetrahedron mesh and my, or not, I don't need my entwine, just my tetrahedron mesh, connect that here. I get my little numbers. And here, of course, we're not using like large planes. We only have 4 planes, 0, 1, 2, 3. And this needs to go away for now. We have our 3 planes. So I'm just going to say, okay, if we start from plane 0 as our root, and our target is plane, can we do plane 0? Can it just kind of grow backwards? We can, but we don't care about that. If our target is plane 1, huh. Ah, not good. Okay. That was 270. Oh, ew. Okay, so we need to find new rotations that actually will work. Sure. I'm just going to do 0 dot 360. So that's 0. It also aligns at 30 degrees. Or not also, it starts aligning at 30. Then it's aligning at 150. And then it's going to align at 270. 30, 150, 270. Okay. It's going to be 30, 150, 270. And then the root is 0. All the other directions is 1, 2, 3. Or other planes. Okay. Let's just make sure that we're not being stupid. So that is also 30. 30 is good. And that means 150 and all other are going to be good. Okay, one more. 30. Yep, 30 is good. Okay, so those are the angles where it aligns. And, well, I guess geometry as an output here and data as an output here. I'm contemplating if I should include the radius. I don't really care about the radius. Cluster this. Call this tetrahedron tile. Again, guide curves. And then output geometry. And plane instructions. Let's see. Let's see if our little library that we're slowly building, if that's gonna work. So geometry connects to geometry, plane instructions connects to plane instructions. We look at the final outputs. Reset. Works exactly as it worked before, but now the logic of how it works is embedded within the element itself. If you're more interested in this, why did it stop? Why did it stop? Did it reach 300? Yeah, it reached 300 steps. Okay. If you're more interested in this logic of characteristics of a structure and the behavior of a structure being embedded either in the overall structure or in the parts that make up the structure, check out mereology. Google what mereology is, check it out. There's a few interesting kind of thoughts in that regard. Okay, we have 2 tiles to work with. Should we add a transformation tile before we finish this chapter? How are we on time? 1 hour. Sure, I'll add this logic, you know, of transformation as well. So first of all, transform percentage and weld all of this we want. Copy paste down here. Don't care about that number. So as a reminder, hide that. And still something there. Why? Okay, no, yes, here. Right, so as a reminder, we have an object that transforms and we have very specific planes of that object that we fished out, that we fished out here, where it's able to rotate. And we're just going to check those out. 2, 5, 6, 9. Those are the planes. Plane number 2 being the root plane. Okay. So from our previous warm-up script, all we care about are these things. So then I will just, the unwelded mesh will connect to the mesh input here. We don't care about the platonic solid from tetrahedral platonic solid input. So we delete that. And then these planes here, I'm just gonna, let's see here. Okay, so I care about plane number 2. I care, that's my root, and then plane number 5 is going to be my target. And it's not really aligning. Neither should it, right? We came to a conclusion that this geometry, yeah, there's no angle where this geometry would be able to align, I think. Oh no. I mean, it's aligning here pretty well. Nope. No, it's not. 140? No. And as it transforms, yeah, the alignment messes up. Alrighty. So that means we end up with 0° or 90° alignment. And then once it's fully, yeah, it's not going to be 90 degrees, it's going to be 30. 150, 270, okay. 30, 150, 270. So it's going to be the same logic as what we had before. I wonder if we can have some sort of a, if we're transforming this, then the angles change. I think we can. Because for transformation at 0, oh, actually the alignment is yeah, okay. At transformation 0, the alignment needs to be 0, 90, 180, 270, for example. And at transformation 1, the alignment is kind of different. It aligns at different angles. I think we can do that, right? Right. So let me borrow that, move to, and actually borrow this as well. Move to the start of the curve part, and so on. Then this is going to be our geometry, right? So I'm just slowly building up the cluster. So that's our geometry part, and then we're moving it to the start of the curves, plural. And then we're going to give it instructions. And the instructions are going to be these planes right here. So they're actually going to be pretty simple, because the planes, I don't really care about the, like, dividing up the planes. So it's going to be 2, 5, 6, 9. Actually, I can just like that. Plane 2 is root, and then others are branches. And then I will need to kind of do like a remap, I think. And then we will have like 3 numbers. So the value, that's going to be remapped is going to be this number here. The source domain is going to be just construct domain. It's just going to be from 0 to 1, because that's where our slider, what our slider is doing. But the target domain then will be actually 3 different domains, right? So at 0, if it's 0, it should be 0 here, but if it's 1, if it's 1 here, then it should be 30, right? Yeah, 30. 0 to 30. Ooh, this is a little bit... Also, I don't want to see that. Okay. And then that's the first angle. Then the second angle is going to be 150, and the third one is going to be 270. Okay, so something to 150 and something to 270. Multiline target. And the something we can check when we have zero transformation. So it's actually going to be 270 for the end, but then 180. 180 and 270. Okay. Okay. And that's the result goes in here. Dynamic. I think we're pushing this a little bit, but that's good. I think it's good to push things. So we end up with a mesh right here, and we end up with data right here. And our input is actually going to be a number like that. And we can just cluster this whole thing. Wait. Yeah, curves, my bad. Curves go in here. Now we cluster. Okay. Name this transforming tile. Number transform percentage. And then guide curve for position. Geometry. And then data. Right. So I'm just gonna make this into a group. Okay, so now we have ourselves third and the hardest tile. Let's take a look at how it behaves. I'm just going to geometry and data go in here. Don't need to change anything else here. Of course, need to look at the preview. Uh-oh. I think that's because it does not have any. Okay, let's see, repetition 0. It has an option to move either to the left, branch out. Right. So it has an option to move to the left or to the right. And also I have noticed that one of them is kind of crooked. Okay, this needs more work. This needs more work. Actually, I'll do that off camera. And then I'll show what kind of a transforming entwine I end up with. But let's just see, even if we have something a little bit kind of messy like that, with the still, yeah. It tried its best. It seems like it's super limited in terms of the angles at which it can grow. But one thing that we need to make sure that it does is when it is a tetrahedron, yeah, when it's a tetrahedron, it just doesn't care. It just keeps going. Okay. So that means all I need to do is just find, that's fun. I just need to find the different angles at which it works, it would work, and different angles for the planes. So for this one, you'll need to give me a second. I'll pause the video. Okay, so I made it simpler. And by simpler, I mean more nodes. So here now it's divided up everywhere. I don't use more than one branch. And for each branch, I specifically looked at the alignment for a cube and alignment for a tetrahedral triangle, right? A triangle from a tetrahedron. And then, you know, it's always root is plane number 2. And the target planes are 5, 6, 9, right? So I separated them out just for like clarity sake and for experimentation sake. So now it converges nicely when it's fully transformed into tetrahedrons, of course. And it also converges, well, poorly, when it's transformed into a cube, because it can only grow that way, right? I don't know what's up with that, but that's what it does. I guess the options for growth are still like that, right? Why the hell are you still rotated? That's the third one, right? Are you okay? Are you kidding me? One, two, three. The third one is bad. Save and close. Let's just look at it here. That's the third one. 53 to 30. Oh, that's because I'm bad. It has to be 270 by 30. Okay. Right. So now that growth is like so, but you can still see that it's linear, right? It can't grow in any other direction except for, this line. That's just a built-in problem issue that we have. But don't you worry, we can still check how it's gonna behave. Yep, still does the freaking line. Anyway, but now the interesting bit begins. This is where, this is not an ideal form for it, but this is where you can kind of start changing the angle, right? Slowly, like transforming these guys. And also as we are transforming them, it still dies when it can't grow, or when it kind of just hits itself. So we can start looking for different transformations where it's actually capable of doing the whole structure. Come on, do your best. No. Considering that it only like uses two, oh my god. It only uses two planes for this. Um, three planes for the growth. We're dealing with a super limited like growth structure. And the thing is that once it reaches the end here, it is unable to branch out because all of the planes are intersecting, right? They're creating an element that is intersecting, so there's no potential for it to branch out until we reach something like that, I guess. Well, this one can't even grow. Come on. Okay, fine. Then it's able to actually branch out. All right, so now we have our transforming tile that is not really doing much. I guess a different kind of geometry is needed for this. So this is our experimentation part at the tile level. And here we have our Tetris block tiles, right? That are doing much, much better. And done. I saw you add one more element there in the back. We'll need to take a look at that. Okay. And keep in mind, like you can always replace the elements with nicer ones, right? So now just to kind of clean this whole thing up, I'm going to group this and I'm going to move it here and delete that. Mesh comes in here, point display goes out here. So I'm just going to make a cluster out of this, because this we will never do it, like we will never change. So cluster, call it plane checker, mesh for both. Okay. I'm just trying to make it as small as possible as I possibly can. Something like that. This will need to be big either way. The angle. And the final one is the orient. Okay. So that's the root. and that's the rotation. Right. Oh yeah, and this needs to be part of the group. Add to group. Okay. So this needs to live somewhere, perhaps here. Everything needs to move a little bit to the right because this is expanding slowly. And I think we're good to go with this. Delete all of the meshes from here. That's fine. It needs to be somewhere here. Don't need to see the mesh here. Okay, we're done. We're done with this chapter. Next chapter is going to be to make sure that if it's failing, if the geometry is failing to find a branch for branching out, it should kind of try and find a different branch, right? Where we're going to have that kind of a logic. So if one branch is failing after the growth, like after it finishes one curve and it branches out and that branch is failing, it should start from another element and start branching out. That's going to be our next chapter. See you there. All right, let's begin with chapter 6. I think this is going to be the last one. And then I'm going to show you a more complicated version of this that I will not be teaching you how to do because it's just, you keep on building on this knowledge that I'm currently showcasing to you. So I'm just going to make another copy as per usual, unbreak it. And here, right, the issue that we currently have is it breaks right there. And the way of how it breaks is actually quite interesting. So that's 47, right? And then add loop number 47 here where it has, if it's near a guide curve, then it should be true. It is true, right? It triggers that it should be near the guide curve, and then suddenly branch position this bad boy, or sorry, not branch position, but find element closest to the next guide curve. This cluster triggers, and this becomes our new element from which, you can see it, right? This becomes our new element from which it's going to try and branch out. And of course, it's going to fail, right? So what we want to do is we wanted to have a logic of if this element fails, no worries. It will just take the same list of elements that we currently have, and it's going to shift that list, and it's going to try a different element, and then a different element, and a different element, right? So it's going to keep on trying to spawn a branch from different elements until it can grow, increasing the possibility, you know, of assembly, I guess, or decreasing the amount of broken branches, if you will. So for this to work, in order for this to work, we need to do a few things for with this. So I think we begin. Actually, give me a second. I don't know where we begin. I need to think about it because it's going to be quite a complicated chapter. 1 second. Okay, let's plan this out. So first of all, I want to go into here and actually name the inputs, or rather the outputs properly. Current gen. D1 was the, is it the recorded gens? No, true counter. It's guide curve counter. Then recorded generations. Then we will need one more, which is going to be branch element counter. And then one more, which is going to be attempt counter. And I think that's going to be sufficient. And for the, I think we don't need this here. I think we can just set data item 0. set data item 0, set data item 0. So we start the counters from 0, right? Now it's freaking out because the inputs and outputs are wrong. So I'm just going to change the, I'm just going to make sure that they are correct. And I'm going to current gen. We need to keep things clean. Recorded gens. Wait, no, it's not recorded. This is recorded gens. That's the, oh my God, guide curve counter. Yeah. Guide curve counter. Okay. Then we have recorded gens. Then we have branch attempt or branch element counter. And last one is branch attempt counter. Okay. So now we have ourselves like a loop. Since the loop is not closed for some of the inputs, it's going to be freaking out, but that's okay with us. So now let's think. So we first of all want to, what do we want to do? We want to remove a branch, remove a set if it can't grow, right? And for that, I kind of want to force, well, we already have the logic of it. Actually, let me just connect these two together so that it's not complaining. And literally, right, it needs to find a new angle from which it can grow or not. So I need to do a few checks. I want to count how many elements we have first in the branch, right? So in order to do that, I will ask for a null item, and I will ask for an OR. The reason why we're going to be doing this is because I'll simply be connecting the, I can do better. 1 second, I'll prepare better to explain this. Okay, if this is null, the closest mesh that is chosen, if that mesh output is null, right? That means our geometry is somehow breaking, our growth is somehow breaking, and it should consider the current branch, which is growing, to be dead, to die, right? So this is one condition. If this is null, if it's unable to produce any offspring, this is false, this becomes true, and this gets triggered, or at least one of the inputs for it becomes true. Also, or literally, or if we reach the end of the curve, right, then it also needs to be, if it's true, then it needs to also reset a counter of how many elements we have in the branch. Right now, okay, bigger picture, step back. Right now, what I'm doing is I want to count for every branch how many elements I have in it. And in order to do so, so basically I want to fill in this branch element counter. I want to have that as a proper number that keeps increasing, but the moment when we reach either an element that cannot grow further, so branch has to die, or when we reach the end of where the branch had to grow to, then that counter needs to reset and start counting elements for another branch, right? Hopefully that makes sense. I can't do better. I can't do better than this. So we have one check for null of the mesh, and the second check if it's near a guide curve. That true check exists here, right? And the last one is, or not the last one, then we'll need a number. And that is just simply branch element counter is going to connect to our number. Right now it's going to be 0. And we will keep adding to the number. Every loop we add 1, but the moment when this is true, again, when either the end of the curve is reached or the branch cannot grow and it has to die, when both of either one of these is true, so filter. Why is this true? Oh yeah, because end of the curve is reached, right? Then actually number 0 should be used, like that, right? So it resets the number, right? And then we, oops, nope, number. Then we feed it here, and we can make this into a little bit nicer cluster, I think. 1 second, I'm just thinking if I need to add anything to this to, no, that's fine. Cluster. Okay, I is going to be, we're gonna call it element can grow, true, false. Then B is going to be, yeah, end of guide, curve, true, false. And then last one is going to be counter, current element amount, branch element amount counter, branch element amount counter. Output is whatever. And the cluster name is going to be counter, or current element counter. I don't, okay. CEC, current element counter. And I'll just group it and name it here. Current branch element counter. Okay. And we have our output here that connects to there. Okay. So now, as this is growing, this should give us actually 0 already, because it's unable to grow, but generation 46, yeah, gives us 47 elements because it starts from 0, right? Okay, so that works. And then at generation 47, it reaches, it can't grow. One of these is true, don't know which one. That is false, and that is true. So end of curve is true. So this becomes 0, and it will force in the next time it rolls over, we're going to start counting again another branch. Okay, so we have a branch element counter. Then I need to be able to remove the branch if it's unable to grow, right? So to do that, I will need to check all of the, actually, let's clean this up a bit. More space. So bad. So freaking bad. Okay, I mean, I do want to be here. I'm checking my notes. Don't worry about it. I kind of want to be here, but that number does not need to exist. Hide that. The wires are super annoying. Okay, we have this, and then I want another one somewhere here, and that node is going, that future cluster is going to actually remove the elements. So I want all recorded elements, so that's going to be geometry input and element recorder. I want that. I think that's fine. Then I want a boolean, and it has to be a boolean from checking if it's able to grow or if it's not able to grow. Do I have any booleans like that or any checks like that? Hello? Not really. So I can just do a simple one, I guess. Once the closest mesh is chosen, I'll just give it a little bit of space. Once the closest mesh is chosen, then I can, actually, you need to be here. Then I can run it through null check. And that's going to be my boolean that I want. You know, is it able to grow or not? And I'll just for this, let's do it this way. It's going to be false. And then another one above it right here. That's going to be true. Okay. That is still triggering a true. Not sure why. Oh, because we're at 47. 48 actually triggers true here. Okay. So that boolean I need to use, and that 48 trigger is happening from the fact that this element cannot grow, the selected element at generation 47, that this couldn't grow, so it couldn't produce the next generation, right? Okay, so we have our like null check thing here, and then we have our end of curve check thing. Then I also want to count how many elements, or rather, no, not how many elements, but yeah, how many elements I have in the branch, right? In the current branch. So I need a number, and that's going to be my branch element counter, which right now tells me 47. Okay. Since it's 47, that means that's the amount of elements that I will need to remove, question mark? Or will I need to just shift the list? We'll see. We'll see. So how do we do this? We take the geometry list that we have, we reverse it, and we will call index. No, yes, call index. And I can just use series, right? Series of numbers. And the amount of numbers is going to be this, but I shouldn't call all of them. So this should be -1, x -1, cancel, x -1, the expression. So whatever this number is, this should be one less, I think. And that's going to be my indices, right? So I'm basically culling. After culling, 3 are left. Why are 3 left? That's a little bit strange. We'll need to take a look at that. Then I reverse the list, and I will reverse it back, right? And then I filter. String filter. And okay, logic is this. If this can grow, if this boolean is false, if this can grow, then it should use just the original list. That's fine. If it can't grow anymore, then it should use the reversed, oh, not the reverse. Yeah, it should use the re-reversed culled list and try again, try growing again. I think that's gonna work. And the output is What is the output? Meshes. Can I just do data? I'm just gonna do data. Okay, I think that's kind of it. That's the cluster. So now let's name the inputs so that is a little bit easier to follow. First one is recorded elements, all of them. Second one is going to be true if can't grow, if there's no options to grow. Third one is branch counter, branch element counter. And output is impossible to change. Great. Can I just... whatever. Recorded elements. Okay. And that, what do we do with it? Well, that just needs to go right into recorded elements input here. Right? I think it does. And then we need to, when we try to grow again, we need to try from a different element. That's the main thing. So yucky. So yucky. Okay. And I should name this, right? Remove branch if cannot grow. Okay. Okay. Next, let's somehow clean this up. I have no idea how, but somehow just try to clean this up. So we have that and that. We also have the curve counter somewhere here. Curve counter? Hello? Current branch element counter? No. Remove branch if cannot grow. Am I dumb? We are counting guide curve counter. Where the hell are you? Okay, that's the guide curve counter. Okay. I'm gonna make you like orange or something, because or that's not orange, but good enough. Just so that I can find you easier later. That number. No, wait, that's just if end of curve reached, right? That becomes true. So it's not that. Yeah, there we go. That's the one. That's the one. That's the one. Okay, that's the curve counter. Green. Okay. This should also be kind of here. I know that this is kind of boring in terms of me just kind of moving things around, but trust me, you want to have some sort of a logic for this. This is, by the way, the worst thing about Grasshopper is just that the user interface is garbage. It has been garbage ever since it, the logic of it, the way you script in Grasshopper is not suitable for heavy scripts. It's suitable for easy, quick little things and C# scripts that you just kind of connect it together and chain together. The moment when you try to do anything with like clusters and more, not Python, not C#, but in actual Grasshopper, it's just a shit show. It's just bad. If any developers of Grasshopper are watching this, look at Unreal Engine and the variables there and how variables are kind of worked with and treated there and how you can cast data and so on, right? Anyway, rant over. We continue. So we have that, and I do want to if we jump to the next curve, then the index that we choose, of this element, we should not shift the list basically. So the index of the element should be reset back to 0, right? The closest element to the curve is chosen. If the moment when we cannot grow from this element, then we should increase a number and shift by that number to get to the next closest element, and then the next closest element. Okay. So I need a bunch of inputs. I need the curve counter from the previous generation. That's just going to be a number. This one. That's the reason, by the way, why I moved it over here, because I need to know at which curve I was at before, right? Before trying to branch out. So this output here. Then I need a curve. Shit. Afterwards. So this one is actually, this is after we add, and this is going to be before we add. So I need one more number. Okay. Again, I can do better. Give me a second. I'll get my ideas straight, and then my mouse is gone. My mouse is okay. Hello? I'm not having a good day. Can I pause this? Okay, I think I know. New mouse, by the way. I think I know how to explain this, or the best approach to be clear about what the hell is going on. So for now, I'm just going to delete these two. We will skip over them, and then we'll come back to once we know what we need. So this, find element closest to the next guide curve, right? What we want from it is not just to always find the same element, but rather also understand which attempt it is to branch out. Currently, we're at attempt 1 and it fails, and then it's going to be attempt number 2. And then from that number, it should select a different type of an element to branch out from, right? So the logic should be pretty straightforward, but let's just go into our branching script. And here we basically just have, we're sorting, right? And we're sorting according to, and we're always getting the first item in the list, right? But I don't want that. I want to have a cluster input. I want to be able to choose which item in the list I'm getting. Maybe it's going to be the second, maybe the third, maybe the fourth, and that's going to be related to the branching attempt that we're going to have. In addition to that, I also, 1 second. No, for now, let's just do it this way, right? For now, let's just, there is one more thing that I will want to add, but for now, we just kind of do it that way. So next guide curve is here. All recorded elements are here. And then we have this is going to be branch attempt. Branch attempt right here. So how do we know which branch attempt it is, right? It basically, we need to check if we managed to jump to the new curve or not, right? If we managed to jump to a new curve, then branch attempt should be reset, should be go back to 0, and we should next time we should try with the first, the closest element to the next curve. If we are failing to jump to the next curve as we are right now, that number should keep increasing, right? So I will want, actually let's do it this way, number. I will want branch attempt counter. I'll want a number for this. I will want a boolean. Kind of a boolean, I guess. Yeah, should be a boolean. Check if can grow. Then I will want a number to check how many curves there are, how many, not how many, but which curve we are at currently and which curve we are trying to get to, right? So it's going to be curve counter before and curve counter after. Okay, I'll just do that. Then we can ask if the curves, if they have changed or not, right? If the before and after has changed. How do we do that? Actually, let me think. So I can actually just ask equality. I can ask if these two numbers are equal, and if they are not equal, then I'll know that it has not failed, but like that it has changed. Yeah, that these two numbers are different, and that means we're at the next curve. Okay, so that's good. So how do we check it? Well, we have our filter here that keeps adding +1, or it doesn't, right? So if it adds +1 right here, this is after, and then before we need to check this input, which is all the way there. A little bit annoying. Let's just do a relay here real quick and then get it from the relay like that. Okay, let me explain this part just a little bit better. So here we have a number before, here we have the number after, you know, the curve end was reached, and the moment when it reaches the curve end, these two numbers will not match up because +1 will be added, and this equality will give us a false, or inequality rather, will give us a false statement. That false statement can be then used to check if we should reset or not, right? So I can reset. I can filter. Oh my God, stream filter. That inequality is used as the mask or gate, as a gate, and then 0 is going to be the branch attempt counter, and 1 is going to be empty. No, it shouldn't be empty, it should reset, so it resets back to 0, right? So it should be 0. Branch attempt counter, by the way, comes from branch attempt counter, this D4, right? Like so. All right, so every time when we reach the end of a branch, we say that attempt has been completed, and we basically reset the amount of attempts that it took so that we can count again for the next branch, okay? And then the counting itself, so that's simple. Filter. Filter. If an element can grow, that means a next element is going to be born. So we simply, where is it? if near guide curve, no, I want the other one, this one, which is currently false, but this, check if it can grow. So if this cannot grow, then this is false, then it shouldn't count +1 because it couldn't grow, right? But if it can grow, then it should be +1. +1. Like that. Oops, wrong one. Like that and like that, right? So basically every time when an element can grow, I'm just adding, sorry, every time when an element can grow, I'm not adding anything to the counter, right? So it's nothing is added, but every time when it cannot grow, I'm saying, oh, I'm starting a new attempt, so I'm adding +1 to it. All right, number out, and then number connects, or wait, is it a number? Yeah, it's a number. And number will simply connect to the branch attempt counter right here. Having fun? Having fun yet? I sure am. Okay, cluster time. No, that's a group. Cluster time. Ooh, it remembers the names. I like that. I like that very much. And this is gonna be called branch attempt. Okay. Let's group this and let's name this properly. Let's just call this if jumped to new curve dash reset, right? If it managed to jump. Else, if cannot grow, or else if, I guess, else if cannot grow, then count I++, add one to the count. Okay, so now we have that number, branch attempt. Remember where we created this empty, like not empty, but this try kind of a node of just finding a new one? I can connect it here. And now we get branch attempt right now is 0. Branch attempt now here is 0. That's okay, that's fine. And then it's filtering out. What if I do 48? Something's off. Branch attempt here is 1. Oh, wait. Is something wrong? 1 second. Current curve is that. What? Hello? You're the wrong side. Okay. All of the meshes, from all of the meshes, this mesh is selected. Ah, maybe that is actually fine. Are we triggering the jump to a next curve? 1 second. Branch attempt, next guide curve. We are, okay. So this also needs to be adjusted, needs to be fixed. Oh, how fun. Okay. Let's just do a... Okay, I need to check my notes. Not sure. I mean, it feels like right now the next curve, the +1, is unnecessary. Next guide curve. Simply because it's not really... Like we're already in the next generation, right? When we're trying to branch out. So we should be using the current curve. Like that. And now it seems like it's creating the correct element, or choosing the correct element. Let's try. Okay. I have no idea what's going on there, but Something is happening. Next curve, I'm just gonna delete. I'm just gonna try and use the current curve for everything. Okay, so do I just call it guide curve? Okay, so here clearly an element is added, and branch attempt, I actually wanna branch attempt, that is still 0. Okay, what if I do 49? Keeps adding elements there and it's 0 still. Okay, that means it's also breaking at 48. Have an element there and it breaks. Okay, because it adds, it takes the wrong curve, so it's branching out from the wrong curve. Yeah. The possibilities for where it is branching from are here. So I do need to find a place where I made the where I made this mistake. 1 second. Okay, I'm pretty certain, I'm pretty sure that most of the stuff that we've done here is correct and pretty clean, even though it's a noodle fiesta. But besides that, I think this logic right here is broken, and right now brain tired, so it's easier for me to redo this rather than to kind of think about what to connect or disconnect. So I'm just deleting the last filter. Right, so here we find the element that is closest to the next guide curve, and that seems to be wrong, right? That element seems to be incorrect because the next guide curve should be this one, right? Or is it this one? But not this one. So that's where I'm currently at. I'm trying to kind of find where this mistake happened, and for now I'm kind of struggling to find it. So I think the way of how we should do this is by, rather than getting a guide curve from here, the current curve, I'll get all of them, all of the guide curves. So let me just create a curve component. Connect that, connect. Let's do it this way, like that. And then this connects here and also connects all the way here, the list length of the guide curves. Like that. And it is going to be a long ass line, but it is what it is. And for the guide curve, I'm just going to connect all of them. Right click, rename guide curves, get in here, and actually save. That's the branch attempt, and I also want the new input, cluster input. Save that. I'll rename this to curve counter. And curve counter actually inside of current generation right here is going to be the one that I want, because here it says 1 while here it said 0. So once it says 1, it's going to give me the correct curve like that. Then I go in, and from all of these mesh endpoints right there, that's the curve. Or curve list, I'm going to use list item. And from the curve list, I'm just going to extract the next curve. Save. And now the element is like correct, kinda. So once that is done, I do want to filter this. And the gate is, again, it's related to if the tile cannot grow or if we have reached the end. So if either one of these is true, then it should use this. If If not, then it should not branch out. It should use the regular one, right? So this or this needs to be true. So I'm using or, like that. The output is true, of course. And I connect that to the filter G input, and this will connect to 1. And 0 is going to be the last item from our recorded element list. Remove branch if cannot grow. So those are our recorded elements, and I'm just going to say, okay, give me the list item from this. But rather than giving me the first item on the list, no, reverse and give me the latest item in the list, which is right here, right? So basically keep on growing, continue growing from where you were. And then that's going to be our current generation, I think. Okay. Let's see. At least we didn't destroy this. So now let's look at the logic. Also let's look at the mess that we have made. I need to name this properly. If tile cannot grow or has reached end of curve, use output 1. Right? So use this. Okay. Custom preview. Like that. And then this presets black and white, just so that we see better, right? So basically use this for the next generation. Generation rolls over 48. Okay, good. So this is now not able to grow. Since it's not able to grow, this produces a null for some reason. Why? Because the mesh is null. Right. Curve and check. Nothing to check with for the curve, so this is null. That's fine. This is still doing its job. That's good. Okay, and then we get 0. So it's not counting the elements. That's good. Branch attempt. It has added 1 to the branch attempt, which means that here a different element is chosen, and it actually gets parsed through to the next generation. Good. And it keeps checking, so it keeps trying. And the generation afterwards, 50. And afterwards, 51. And I think, yeah, eventually it finds. Okay. Jesus Christ. Okay, so let's keep going. It's not removing correctly. But it is working, at least partially. Come on, keep trying. Okay, sure. Ignored that whole bend, but managed. So here, there was some issue with the removal. I want to try and see again. Around 90-ish. That all was fine. Okay. So here it's kind of growing, 86, 88, 90, 92. Okay, 90, 91, I guess, is where it breaks. Yes. 91 is where it breaks, and let's see. So that's empty, empty, again, null and true. Huh. That's a very strange place to choose the new branch attempt from. Why are you doing that? We're not removing all of the branches, are we? Or branch elements, are we? Hmm. Okay, what do we have as an input? That's correct. Or rather, that's fine. So the logic is remove branch if cannot grow. The problem is somewhere here. Cull. After culling, it's there. Huh. So after culling, it's there. So that's fine. So why the hell does this choose an element that we don't even have? All recorded elements comes from the element recorder. Okay, my bad. Connects here. I forgot that we need to use the removed version of the element recorder with the removed branch. Okay, we try again. Okay, keep trying. It didn't remove. Wait. It kind of kept one element there. This is way too restricted in terms of geometry. Okay, I don't like it that it kind of kept one element there as like trash. That. So that tells me that the branch counter, is that the -1 that I added? That's messing us up. Nope, not here. Is it here? Nope. I'll find it. Yeah, is it because it's this one? So if this is 1, it's actually 0, so it removes less elements. Okay. Am I just being stupid and I don't need to do this? Try again. Yep. Sure, but that's I can live with that. Okay. Okay. I'll explain what I did. So here under however this cluster is called, remove branch if it cannot grow further cluster. So in here we have this issue. We had this issue of series counter to be set to -1, and that's because I was scared of culling too deep in and then slowly kind of destroying the structure as it's attempting. But it doesn't seem like we need to do that. Since we don't need to do that, I just removed the expression and it seems to be behaving correctly now. All right. So that's the logic. Now back to the to my Tetris tile. We're kind of done here. There's going to be one more chapter of me showing you the final boss of this, and the final boss is only going to be available to Patreon supporters, and it's not going to be a part of the like tutorial. It's just going to be literally my research script that I have that I'm just gonna share with the people who support the channel. but that's later. For now, I'm just adding more flexibility to the system to just make sure that it, yeah, now it behaves perfectly fine. Okay. So now with this, we can build whatever structure we want. I'll need to think about how to make this into a nice, like a thumbnail, thumbnail thing. Probably the answer is just resolution, right? If I just have these curves, insert. If I just have these curves and I just take Alt key, rotate upwards, move it up, something like this. And I just grab all of these, set multiple, and just let it grow. Yeah. With the amount of resolution that we will be able to generate, this is going to look pretty good. Did we reach the end of the... Oh yeah, that's too little. Okay, so next chapter is just going to be a showcase of, you know, this but on steroids, and then I'm just going to give you some final thoughts about this whole thing, and we're gonna call it a day. Hope you enjoyed this one. I sure haven't. I like to do watercolors, you know. I like photography, watercolors, art. Life. Anyway, see you in the next chapter. All right. All right. So final chapter. I don't even know which one it is, but it's the final one. So here I'm just saving this as chapter 6. 6. Right? That whole logic is here. It's as clean. I mean, this Noodle Fiesta is as clean as I can get it for this course. We can make it cleaner, but that's gonna be later, or not later. You can do it yourselves. I think moving things around and then just finding like logic for how you can group up things, that just helps in understanding the script that you are working with. Did I save this? I don't remember. I'll check. I have. Okay, that's good. So I'll save this again, just in case. And also I'll internalize my curves and save this again. Okay, close that. And now we can look at the next, like, there is a certain limit at which I cannot do a course about a single video course about a subject, right? There's a certain limit at which we would need to actually have a semester, like a proper semester with the students, you know, sitting down and learning things. So in this case, that's the reason why there's a cutoff in terms of the complexity of the script, and the cutoff is at chapter 6. But if we had a whole semester, at the end of the semester, you would have, or we together would have something like this. That, what the hell is that? That's a mesh. Will anything break if I delete this? Nope, nothing broke. Okay, so we would have this. Does not seem like it's anything cool, right? It just kind of grows and adds a weird thing at the end, a weird little leg. So now let me try and explain to you what the hell I was thinking of here. So first of all, we have different tile libraries: voxel tile library, non-voxel tile library, 2D voxel Tetris tile library. So I can change them, right? So this is voxel, this is non-voxel, and this is Tetris. Non-voxel already kind of introduces us to a little bit of, huh, That's very curious. That's very interesting. You know, why is one element a little bit different? Glad you asked. If I change the guide curve, like I have multiple, of course, here, to a different 1D curve, I should probably be showing you how those look like. 1 second. Here we have the tiles. Da, da, da. Yeah, that's good. And then I want, yeah, the curve to just be visible. So, again, play. We don't use one element now. We're using a library of elements, as you can see here. Multiple clusters are entwined into a dataset called tile library. Each of these clusters contains, well, an old element, but contains the creation of the tiles as well as the possible rotations of the tiles, right? So the logic for how the tiles are made. In this case, this library, the non-voxel, is made out of 4 different elements. Here we have 6 different elements, and here we have 8 different elements. So actually, let's look at the, this is voxels, and this is Tetris, right? So we have multiple, like, different elements here. Let's do voxels for a bit, like so. When you have different shapes, you can approximate the curve that you have drawn much better. 2D. 1 and 2. That's the branching behavior, right? Again, the two lines. Oh, right, my bad. I should just show you these guys, like that. The 2 lines are here and here, right? 2 parallel lines. Perpendicular lines for branching looks like that. Very simple. 2D grid looks like that. It's capable of you know, jumping around. And all of this logic that I'm showing you right now, we already know. We already have built it up. We already have built it up with our datasets, with our scripts. This is just like the next step of it, which also is a little bit trickier. So for example, this, right? And when we are working, you know, with stuff like this, we can then start thinking about how this would be built, how this would be actually structural. For example, here, right, this is definitely an issue. So an additional kind of member would need to be added, and you can either add it manually or you would need to add it like properly with the freaking within Grasshopper, right? With additional functionality. I don't remember what this is. Oh, that's just a box. Okay. Well, twisted box. And what is this? That's something also very simple. Right, so that's one. Then let's just do a pavilion for these. Don't really care about these 2 curves. Can delete them. Right. And then if I were to, so 1 second. Someone's calling me. Right, call over. So where was I going with this? Pavilion, right? Possibilities to create pavilions, possibilities to experiment with different elements, and generally, you know, continue experimenting, because this is where I came, what I came to, and this is where I finish my kind of tests and so on. So again, if you want to have this script, which is much cleaner, but you'll notice it does have a few things that we have learned in this course. But if you want to have this final script with all of the library elements, link in the video description below. There's going to be the Patreon link. Also, you can be a YouTube member. If you're a YouTube member, you also get all of the files that we do on this channel for free, considering that you are supporting the channel. With that out of the way, I just want to talk about generally about the purpose of Grasshopper, and where I think it fits and where I think it doesn't fit. So as I am kind of experimenting with these elements, the main issue or the main thing that I'm constantly reflecting on is the control, the amount of control that you have and the amount of transformation that that control needs to take before you reach the final result, right? So to translate it, how much effort or how big of an effect does Grasshopper have on your project? Stylistically, be it in terms of what you can do and so on, right? Because again, growing something organic or whatever, sure, you can do that. But then the moment when you need to introduce a structure or a logic to it, that becomes much, much harder. And that's why, this kind of logic-based course, I consider it to be somewhere in between intermediate and advanced level course. So Grasshopper is great at system creation, but it's not that great at, customization, I guess, or adding tailored, in this case, elements or solutions for any structure, right? So if I were to say that, okay, this structure is great, but I only need this to be, I don't know, like these two parts to be connected, manually modeling that out is super easy. But with Grasshopper, this would be such a long process and such a long journey, right? So one of the things that I notice from at least beginners, I'm not sure about you as an intermediate or an advanced level user, but beginners tend to try and use Grasshopper throughout the whole process, and in doing so, they actually lose they lose control. And this is coming back to the control and then different ways of how to introduce control that I was talking about before. And tying yourself to a single tool is never a smart idea, especially if that tool only operates through systems, like through different systems and through different, not approaches, but what was the word? Like logic, chaining of logic, right? Because you'll end up with just having a really bad time when you'll try to customize it. Blah, 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 right? I'm blabbing a little bit about this, but the reason why there's underlying curves, right? The reason why there all of this attention to how two elements meet each other and how do they arrange and trying to search for structural loops within the system and so on, all of that relates to at least my drive to make these structures not just pretty, or interesting, looking cool on the screen, but actually buildable. And there are certain limitations and certain level of control that you need to have to make these structures buildable, right? To make these structures logical. And that's my main kind of suggestion for you as a Grasshopper user is to make sure that the input that you are using, that the input that you are starting from at the beginning, enables you to have the highest degree of control over the script, over the software as you can, right? So don't try to run everything from a single slider. Don't try to run everything from I don't know, like a few variables. It, of course, it depends on what you're doing, but most of the time for more complex stuff, it won't work. You want to have a greater degree of input to receive a greater degree of control to then get closer to something being actually driven, a design being driven to something that is real, right? That can be actually made. In this case, apologies. In this case, I still consider this not to be buildable. I mean, it can be buildable. It can be built, of course. It's simple enough to be built, but there are still moments and issues and so on with it where it just wouldn't work. But the nice part about it is that I can just simply, let's do, 1 second, please hold, unplanned. Let's just do Helix. Sure, whatever. Just kind of twist it like that. And then make it a bit smaller. I can always, fully control where I want the geometry to be at. And that enables me to actually fine tune the structure that is grown from the geometry. It's really freaking out. Okay, it is really freaking out that the endpoint is right there, right? So it's really not steering that well. Oops. But for example, here, if I rebuild, if I rebuild this and I give it 50 points and degree of 1, let's give it like 150 points. What? Did this crash? Welcome to Rhino 9, the work in progress version. Let's open this again. So I'm blabbing now a little bit, I know, but bear with me. You need to be very mindful of the inputs that you choose, because those will either lock you down to certain solutions that Grasshopper, has, and then you won't be able to alter those solutions. Or even worse, it will just shrink the level of possibilities, like possible outputs that you can generate, right? So I think that's the main. I really don't care about the recovery file. Close that. Okay, back to here. So, here we're driving everything with lines and with curves and with element behavior, but then adding more and more inputs would be good, would help us. We don't have time. I am really struggling to find the freaking helix. Hello? Helix, there we go. Okay, that's a spiral, that's a helix. And I'm just gonna do that and then scale this up and then rotate this like that and then do this, whatever. And then I can rebuild again, this time, okay, 100 points, degree 1. Okay, this time it works. And I can grab it as a curve, set 1, explode. Nope, not the tile. Explode the curve so that you get the segments. This is me also showing you, how I would treat that problem that we had. And now it's properly going to run through this spiral, right? It's going to be a little bit slow simply because we are, the collision detection cluster is a little bit on the heavy side, the mesh intersection. I think that's because we are branching out so much that it's checking for too many things. We have so many tiles that we're potentially growing out from. But if I have a smaller library, it's actually done pretty damn fast, right? So that, I hope you've enjoyed this course. I know that this course was not as straightforward as the one that we've done with the Grasshopper for Beginners course. Neither should it be straightforward, because it is a much more complex thing, and it also assumes that you know a bunch of things, right? Already, so I skipped over a few. This script available for patrons. I already said this. I won't keep looping. Use Grasshopper with other tools, in tandem with other tools. Don't just script, don't just use Grasshopper. You're locking yourself out of the whole range of possible designs that you could do. And have fun with it. I'm tired. I'll see you in the next one. Later.